Hello students, welcome to the another session of Champion series. My dear students, ma'am is here with yet another interesting chapter. That is your coordination compounds. It is one of the most important and the most interesting chapter of inorganic chemistry. And today, you and me together are going to excel this chapter. So, my dear students, what are we going to study about coordination compounds? First of all, in this chapter, we will be discussing what are coordination compounds, which are compounds are to be identified as coordination compounds. Then we will study what are the properties of coordination compounds. What happens if we try to put them into aqueous solution? How many ions do we get? How the ions get dissociated? All these things we are going to discuss. Also, we are going to discuss the nomenclature. Yes, it is exactly like the organic chemistry. You name compounds. Similarly, you actually name compounds in organic chemistry, in coordination compounds as well, and it is super interesting. Later, we are going to discuss about the various theories regarded to the coordination compounds. And then, my dear students, we are going to we are going to also understand what are the different types of isomerisms that we can see in coordination compounds. So, if you notice, there are a lot of things similar to organic chemistry, right? Yes, that is the reason I find this chapter the most interesting chapter. So, my dear students, let's start the amazing session. Now, if we talk about the coordination compounds, my dear students, you have to understand the various types of salts. Before this, I would like to make you understand the different types of salts. We know a very basic type of salt. Ma'am, we know that we have learned in class 9th and 10th as well that NaCl is a type of salt. Yes. You also might have heard, my dear students, that NaCl is a strong electrolyte. Yes, ma'am. NaCl is a strong electrolyte. And what do strong electrolytes do? They actually dissociate completely into their aqueous ions. So, my dear students, if I put it into some aqueous solution, I will get Na plus as an individual ion and Cl minus as an individual ion. Right? Yes. So, this is a type of what? A simple salt. So, what are you going to say, ma'am? This is a type of this NaCl is a type of this is a type of simple salt. Right? Yes. There are various types of salts, my dear students. Now, I am going to tell you something about what is called as double salt. Double salt will have two different types of salts together, right? This means that when two types of salts are mixed together, you actually get double salts. Okay, ma'am. So now we are going to understand about this. This was the first type of salt. The other type of salt is double salt. Okay, perfect. Let's talk about double salt. Okay, what is double salt? Ma'am, you just only told that when we add two different types of salts, types of simple salts, we get a double salt, right? Yes. So, what would be a double salt? If I add, let us say KCl, if I add KCl with MgCl2 dot 6H2O, what will I get? You will get, my dear students, KCl MgCl2 dot 6H2O. Right? Now, my dear students, this is actually your double salt. That is a mixture of two different simple salts will give you a double salt. Right? Yes. Similarly, you get another type of mixture if you add two simple salts, that is known as the complex salt. So, the next type would be, third type would be complex salt. Complex salt. Okay. Now, what are these types of salts? Let us understand. If you talk about complex salts, my dear students, then what do you get? You actually add two different types of salts, two simple types of salts, but you don't get complete double salt. You get a complex salt. And what is the difference between the two types of salts? That ma'am is going to explain, right? In this type of salt, you get a mixture something like K4Fe. Okay, you get something like this. So now we are going to understand what does this mean. Okay, my dear students. Okay, see here when I talk about the double salt, you only have to focus here. What will happen if you see what I told you? I told you about the simple salt, that if we put it into aqueous ion, you get all the ions individually, right? Yes. Now, if I put a double salt into an aqueous solution, what will I get? I will get all the ions individually. That is, if K plus is an ion, I'll get that, plus Cl minus ion. Yes. You have here also Cl minus ion, so that would be incorporated into this. Perfect. Then you have MgCl2, right? Mg2 plus. Perfect. This is how you actually get, on adding the double salt into an aqueous solution, you get all the individual ions accordingly, right? Yes, that is, all the ions will be completely dissociated. That is known as a double salt. Now, what is a complex salt? In case of a complex salt, I have given you an example. You add two simple salts, you get this type of mixture. What will happen here? If you put this solution into an aqueous solution, if you add this complex salt into an aqueous solution, you will get K plus ion. What do we expect next? We expect that we will get Fe plus 2 ion, and I expect that I will get Cn minus ions as well, right? Yes. But my dear students, this is actually not the case. This is actually not the case in case of complex salt. Rather, what do you get? You get only K plus as an ion, and you get this complete ion. Fe, Cn6, 4. Right? Yes. This is how you actually get the ions. This means that, ma'am, the whole complex salt is not dissociated into its individual ions. Only a few ions are actually dissociated, and the other ions are left. How do we know that in an aqueous solution have the ions been completely dissociated or not? My dear students, you check it out by various chemical testing methods. That is, there are various methods to test whether this ion is present or not. Every ion has its individual test reaction procedure. You apply that in that solution, and you actually come to know that whether this solution contains this ions or not. So all this which I told you is actually experimentally determined, that a complex salt does not dissociate into its complete ions. It only gives a few ions and not the other. Which ions are given and which ions are not given, that we are going to discuss in this particular chapter. Okay, I hope you got this point, the basic difference between a simple salt, a double salt, and a complex salt. Now we are going to read the theory. When two or more simple salts are allowed to get chemically combined, my dear students, they do get chemically combined together in a fixed proportion by weight, then molecular or addition compounds are formed. Depending on their behavior in solution, see, they behave differently in the solution. Either they get completely dissociated or they get partially dissociated, right? Yes. So depending on their behavior in solution, they are classified into two types. One is your double salt and the other is your complex salt, or you may call it coordination compounds. Okay, perfect. Now we are going to talk about the double salts. I told you everything, now you are only going to revise. Constituent ions don't lose their identity. In aqueous solution. Its aqueous solution gives a positive test. See, it gives a positive test of all its constituent ions. Positive test of all its constituent ions means that if you know that you are adding a salt which contains K plus Cl minus ions, and if you test I told you that every ion has its individual test, and if you apply those tests in that solution, you will get a positive result. This means that the ions have been dissociated into their individual part, right? Yes, so you get all the ions. So this means that all the ions are present. Positive test means all the individual ions are present in the solution. They have completely dissociated. Double salts will get completely ionized into its constituent ions. I hope you got this point. Let's move forward. Next is complex salts, means your coordination compounds. This will not give positive test for all the ions because only partially few ions will be dissociated. So components may lose their identity in aqueous solution. They lose their identity. Obviously, you know that you've added K plus, you've added Cn minus, you've added Fe2 plus. You'll test, but you will not get the positive test for Fe2 plus and Cn minus ions. Why? Because they are present in a compound. They are not individually present in the aqueous solution. They've not dissociated, right? Yes. So components may lose their identity in aqueous solution. They don't get 100% ionized. They don't get 100% ionized in the solution into its constituent ions, right? Perfect. Let's move forward. Now we are going to talk about the representation of coordination compounds. Please don't go on the spelling. Sometimes there are a few typing errors. So yeah, there are a few typing errors. Just bear with it. I know compounds spelling is wrong. So please don't comment, ma'am, compound spelling is wrong. Compound spelling is wrong. I know. Okay. Okay, let's move forward. Now, ma'am, you told us about the coordination compounds. We know that they don't get dissociated into their individual ions, but why? And which ions will be dissociated and which not? I am going to tell you that. My dear students, whenever you talk about the coordination compounds, it is always and always represented as something like you have A, you have M, you have L, N, X, plus or minus. Okay, either it could be like this or it could be like M, L, N, X plus or minus, and then you will get A here. Okay, so now let's individually understand each and every term here. Okay, now if I talk about A, in first case, my dear students, A is your cation. Okay, always and always you represent a coordination compound. First you represent the cation and then the anion. Okay, yes, not only in coordination compounds, in fact everywhere we first write the cation and then the anion. So in first case, ma'am, A is the cation, and my dear students, this whole part is actually your anion. So you will say that M, L, N, X plus and minus is my anion. Okay, and now in this particular form, if you talk about these square brackets, those are referred to as your coordination entity, coordination spheres. These two lines are actually called the coordination sphere. So what are you going to say, ma'am? This is known as the coordination sphere. Okay, okay, the ions or all the part which comes into the coordination sphere, that is never ionized. Okay, only the coordination sphere and the cation or the anion part, they will get into the aqueous solution, they will get ionized, but the entities in the coordination sphere will never get ionized. Okay, they will stay intact. So this is your coordination sphere. Here, my dear students, M is actually your metal. Okay, yes. Here if I represent L is your ligand. And what is ligand? My dear students, actually metal accepts electrons. And who gives electron to the metal? And ligands give electrons to the metal and they form a coordinate bond. What is a coordinate bond? You have learned in chemical bonding. I know that. What are coordinate bonds? Whenever all the two electrons are donated by one particular atom, it forms a coordinate bond. So ligands form a coordinate bond with the metal by donating their two electrons. Okay, what is N? N is your number of ligands. N is your number of ligands. Okay, yes, how many ligands are attached? That is your number. Next, if you talk about X, my dear students, in this case X will be negative sign. I hope you understand this, because its value would be negative and its value would be positive. Here this would be positive, so let's represent it like that only. This would be positive and this would be negative, obviously, right? So what is X? X is the charge. X is the charge. Okay. And my dear students, everything would be same. Just in this case, what will happen? A will be your anion and the coordination sphere and the entities inside the coordination sphere would be your cation. Okay. Yes. I hope you got this. Yes, ma'am. Now we are going to talk about individual terms which you will be coming through in the coordination chapter. Now let's move forward. The first and the most important is coordination entity. All the entities which comes into the coordination sphere, this sphere, M, L, N, X, plus or minus. This is your coordination entity. Okay, now let's talk about this. A coordination entity constitutes a central metal. Which is your central metal here? Ma'am, this is a central metal which actually accepts electron, right? Yes. Or ion, it would be a metal or an ion bonded to a fixed number of ions or molecules. Ligands. What are ligands? This L is your ligand. This actually donates its electrons, forming a coordination, forming a coordinate bond. Right? Clear. Very good. Let's move forward. Next is your central atom or ion. It is the central metal which actually accepts the electron, right? So now we are going to talk about individual things which are present in the coordination sphere. First is coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical fixed arrangement around it is called the central atom or ion. Clear? No issues? Perfect. Let's move forward. Central atom or ion accepts electron pairs. I told you they accept electron pairs. Okay? Yes. They accept electron pairs from the other molecules or ions. How does this happen? Here will be a metal and here will be a ligand. Not even one ligand. There could be 4, there could be 6, there could be how many? Whatever. I'll tell you how, on what does it depend that how many ligands are to be attached. Okay. If we talk about one ligand, it will donate its 2 electrons and form a coordinate bond with the metal like this. Perfect. So central atom or ion accepts electron pairs from other molecules or ions, ligands. So central metal, see, central atom actually, the atom or ion which accepts electron. What do we call them? We call them Lewis acids. So here this metal is your Lewis acid. Why? Because it accepts electron, right? And if this is a Lewis acid, because it accepts electron, what will be L? Lewis base, because it donates its electrons. So we will call it as a Lewis base. Clear? Perfect. So generally D block metals acts as a central metal. Why? This is a very important line for you, my dear students, that D block L metals actually behave like your central metals. Why? Why is this case? Because you know that a metal accepts electrons, so it should have vacant orbitals. Yes. And D block elements have vacant d orbitals. Vacant d orbitals. That is the reason generally D block metals always act as the central metal. Now, small size. I hope you understand this. The most important thing is small size. The more the small size, the more would be the tendency to accept electrons. Next is your high nuclear charge. Of course, they'll have high nuclear charge. And the most important, availability of vacant d orbitals. This is the most important reason why they behave as a central metal, vacant d orbitals. Right? Yes, you can be asked these questions in the MCQ form, so you need to know. Let's move forward. Next is your ligands. Now, ma'am, we know very well that what are ligands? They are Lewis bases. They donate electrons by by forming a coordinate bond. So you know everything, right? Yes. So now let's discuss about this. Electron-rich species. They are electron-rich species. That is the reason they are behaving like ligands, right? Yes. So electron-rich species which can donate electron pair to the vacant orbital of the central metal atom or ion through the coordinate bond is called ligands. Now, the question is, which all ions or atoms or elements can behave as ligands, which will have a lone pair of electrons? Yes. So, what can we say? Ligands could be, ma'am, they could be negatively charged. The ions which are negatively charged, they can behave. Yes, ma'am, they can behave as ligands. They have extra electrons. They can donate them. So, ligands could be negatively charged. They could be neutral. If they are neutral, they need to have lone pair of electrons. It need to have lone pair of electrons. Also, my dear students, there are a few which are positively charged but still behave as ligands. So, ligands could also be positively charged. So now we are going to see all the different types of ligands. Okay, positive, negative and all we are going to see. And every ligand has its particular name, which we will be using it in its nomenclature. Okay, so now let's move forward. Here are on the basis of charge, the way you classify the ligands on the basis of charge. The first I told you is negatively charged. So negatively charged, you can see OH minus, NH2 minus, NH2, O2 minus, F minus, O minus, Cl minus, right? So all these kinds of ligands act as your negatively charged ligands, right? All the halogens, oxygen, OH minus could also be act like a ligand, right? Is it written here? No. OH minus, no, OH minus is written, NH2 minus, my dear students, just take it as O2 minus, F minus and just remove it like this. Cl minus, I minus and so on, right? Next is neutral, my dear students. You will call them neutral. Okay. Neutral ligands, NH3, amine is a neutral ligand, my dear students. If you talk about carbonyl, CO, it is a neutral ligand. Phosphine, PH3 is a neutral ligand. Okay. OH minus, NH2 minus, NH2 minus, O2 minus, F minus, Br minus, Cl minus, etc. So many ligands. We are going to name every ligand properly. So don't worry. Okay. Next, we are going to talk about the positives. Then you will see NO plus. NO plus acts as a positively charged ligand. Okay. Perfect. Let's move forward. Don't worry. You don't have to memorize them. When I'll give you their names, I'll actually tell you how you are going to learn all the ligands. Okay, perfect. Let's move forward. Don't worry, don't learn them right now. Next, now, if you want to classify the ligands, they are also classified on the basis of their denticity. And what is denticity? Actually, denticity is that how many electrons a particular ligand is donating to the central metal. For example, if I have a ligand, if I have a metal and I have a ligand who is donating only a pair of electrons, then it is a monodentate ligand. If it is donating from only one side and it is only donating 2 electrons. Okay. Next, if I talk about a ligand, let us say this is one ligand and it is donating one lone pair from this side and one lone pair from this side. It is actually a ligand, only one ligand which has 2 sides and it is donating from both the sides 2 different lone pair of electrons. So my dear students, it is a bidentate ligand. Okay, so what is denticity? How many lone pair of electrons have been donated by the particular ligand? It could be 1, it could be 2, it could be 3, it could be 4, 5, 6, n number of ligands, n number of donating sites. Okay, so now we are going to study about that. What are monodentate? Only a lone pair, only one lone pair is donated. What would be didentate? Ma'am, two ligands, right? Two different lone pairs from one particular ligand from two different sites, donating sites. Polydentate more than two would be called as polydentate. Then would be ambidentate. Now denticity. What is denticity? Okay, I've written bidentate. Bident. Okay, sorry. Okay. Denticity. Number of bonds, coordinate bonds formed by the central atom by a ligand is known as denticity. Obviously, if it is donating one lone pair of electron, you will have one coordinate bond. If it is donating two lone pair of electrons from two different sides, so you will have two coordinate bonds. And similarly, you number of coordinate bonds. Denticity, number of donor positions in ligand. See, I told you, perfect. Let's move forward. What is next? Next is, my dear student, chelate ring. What is chelate ring? My dear students, you know that a ligand can have one donating site, it can have two donating sites, it can have three donating. When it has different types of donating sites, what is formed? Now I am going to help you to understand that. See, if you have a metal and you have a ligand which has L1 donating site, then it has L2 donating site, and then it has L3 donating site. Okay, it is one particular ligand which has three different donating sites. Now what will happen? And this will donate its electrons and form a coordinate bond. This will donate its low electrons and form a coordinate bond. And ma'am, this will donate and form a coordinate bond. What can you see? You see that a particular ring is formed here, a particular ring is formed here. This is actually a chelate ring, and a chelate ring actually provides stability to a complex. It actually provides stability to a complex. More the number of chelate rings, more will be the stability of the complex. Okay, so you need to see that how many chelate. If there is a chelate ring and one molecule is there which does not have a chelate ring, then there obviously the chelate ring one would be more stable. But then if you have two molecules which both have chelate rings, you have to see the more the number of chelate rings, the more the chelation, and the more would be the stability of the complex. Okay, yes. So now my question to you is, does a monodentate ligand form chelation? Can it show chelation? Monodentate ligand means it can only donate one pair of electrons, it has only one donation site. And ma'am, if it has one donation site, it can never form a ring. And that is the reason it cannot form a chelate ring. If I talk to you about a ligand which has two donating sites, if it has two donating sites, can it show chelation? Yes, ma'am. How many chelate rings? Only one chelate ring. See, M, you have ligand 1 donating site, you have ligand 2 donating site. It can form only one chelate. If a ligand has 3 donation sites, it forms 3 coordinate bonds. Then you have metal, you have ligand 1, have ligand 2, you have donation site 1, 2, 3. So ma'am, if I see, then it forms 2 chelate rings. This means that whatever is the denticity of a particular compound, whatever is the denticity of a particular ligand, denticity minus 1 will give you the number of chelation rings, right? So you can write that number of chelating rings, I'll write chelate rings, is always equal to denticity minus 1. Okay, whatever is the denticity of a ligand, minus 1 will give you the number of chelate rings for a particular ligand. Okay, yes. Now let's move forward. Now we will read. When a di or a polydentate ligand, important my dear students, only di and polydentate ligand, they are not talking about the monodentate ligands. Okay, uses 2 or more atoms to bind a single ion and produce a ring, then this complex is called chelate complex. I showed you the chelate complex, and the process of chelate formation is called the chelation, and these ligands are known as chelate ligands. Perfect. Chelating compounds are more stable than the others. right? Yes. 5 and 6 membered rings are the most stable. Obviously, they would be most stable. Again, spelling, spelling, spelling. So I am giving you a disclaimer. Don't don't write in the comment section, ma'am, spelling is wrong, spelling is wrong. I know, my dear students, you know very well English. So don't please don't make fun of these spelling mistakes. They are genuine mistakes, right? We type a lot, so there are genuine human mistakes. So don't write that. Okay. Now let's move forward. Example are diethyl triamine. What does diethyl triamine stand for? My dear students, diethyl, this means that you have a nitrogen atom, okay? You will have a lone pair here, then you will have one carbon, then you will have one carbon, and NH2 would be this side. Then you will have carbon here, you will have carbon here, and then you will have NH2. Just write the valency, H2, and this would be H2, H2, and H2, right? So how many donating sites does this diethyl triamine has? Ma'am, it has one this donating site, one this donating site, and one this donating. So the denticity is 3, and it will form how many chelate rings? 2, right? Similarly, triethyl tetraamine is your homework. This is your homework, my dear students. You have to find its structure on your own, okay? Find its structure, find its denticity, and find how many chelate rings will this form. Okay, so this is going to be your homework. Let's see how many of you answer me in the comment section. Okay, let's move forward. Next, if we talk about the ambidentate ligand. What are ambidentate ligands? You've heard about ambidentate people. I hope you've heard this word, that that particular person is ambidentate, right? That means that a person who can write from by both their hands, right as well as left, they are actually called as ambidentate. I guess ambidentate or something related, ambidextrous, not ambidentate. I am talking about ambidentate. I just said ambidentate. It's ambidextrous. Yes. Who are the people who are known as ambidextrous? The people who actually can write by both their hands, right as well as left, right? Yes. So ambi word is that from this side or that side you can do a particular work, you can use ambidentate word, ambi word. Okay. So when we talk about the ligands, we call it ambidentate. If a ligand has two different donating sites, but at one particular time it only donates from one side, that are known as ambidentate. What is the difference? Let's talk about this. Imagine you have a particular ligand which has two different sites of donation, right? There are two possibilities, that you have a metal. This particular ligand, what will it do? It can use both its sides and donate both the electrons at the same time and form a chelate ring. This is possible, yes ma'am. And this would be what? This would form a chelate ring, right? But what happens if you have a metal here and you have ligand 1 and you have ligand 2, but only ligand 1 donates and not the ligand 2? Only ligand 1 has donated the electrons and not the ligand 2. At some other compound, at some other metal, let us say M2, ligand 2 donates its electrons but not ligand 1. Okay, these are the possibilities. Then in this case, my dear students, it is known as ambidentate. It means that it has two donation sites, but at one particular time only one ligand is donating its electrons and forming only one coordinate. Those are ambidentate ligands. But what are the chelate complexes? In case of chelate complexes, ma'am, what do they do? If it has two different donating sites, both of them donate their electrons at the same moment and form a ring. That is the difference between ambidentate and chelate complexes. Okay, so now you can understand this. Ligands which can ligate through two different atoms, they can donate through two different atoms present in it, are called ambidentate ligands, but they donate only from one particular site. Example, my dear students, if you talk about NO2, in NO2 ligand, it either can donate from N side. This could be your donating ligand, donating position, or what can be the possibility that ONO, you write it like this, and what happens? This oxygen donates. So, ma'am, in NO2, there are two different sites, either nitrogen or oxygen, but at one particular time, only one will donate, and those are known as ambidentate ligands. One more example, my dear students, you have thiocyanate, SCN. SCN has, my dear students, two donating sites, this or nitrogen site. Okay, so it depends that which particular site is actually donating the electrons, and you name them accordingly. I give you how you actually name them. Perfect. Let's move forward. This is known as thiocyanate. This is known as isothiocyanate. It is given here, but you don't have to just memorize it. Next. Next is coordination number. What is coordination number? Now we are going to understand this. Total number of electron pairs accepted by a central metal atom or ion. A central metal has, let's say, 6 ligands and 6 of them are monodentate. So obviously it forms 6 what? 6 coordinate bonds. So the total number of electron pairs accepted or the number of coordinate bonds by the central metal atom or ion from the donor atom ligand into vacant orbital through coordinate bond is called the coordination number. Right? Let us say I give you an example of K4FeCN6. Okay, I am giving you one more example of, let us say, K4FeEN whole rise. Okay, I have given you these two examples. I only just made it, so just don't find any mistakes. What I want to tell you is that if you have these two different complexes and I ask you what is the coordinate number, you would say that, ma'am, here if I see, then iron, what is it doing? Ma'am, Fe, you have Cn, you have Cn, you have Cn, you have Cn, and Cn. And ma'am, it is donating its electrons, forming one coordinate bond because it is a monodentate ligand. So, ma'am, coordinate number would be 6. Right? So, ma'am, coordination number would be 6. What is the case here? If you talk about FeEN whole thrice, what would be the possibility? Let's see. Don't write it K4. Just talk about this particular part. What will happen? I'll write it by color. You have Fe, and my dear students, En is ethylene diamine. En stands for ethylene diamine. This means that you have carbon H2, then you have NH2, you have NH2. So this is what 1, 2, 3, 4. Yeah, 1. Yeah. So here, if you see, then you have two donating sites, one this nitrogen and one this nitrogen, and both of them donate at the same time. So they have the denticity of 2. They form two coordinate bonds. So, ma'am, one En gives 2 coordinate bonds, and how many En you have? 3. So this means that you can write it something like this. One bond, 2 bonds. Similarly, 4 bonds, and 5 and 6 bonds. This means that I can say that coordination number would be, what is the denticity of this ligand? 2. Yes, ma'am. And how many ligands are present? 2. 3. So 2 into 3 will give you again 6. So the coordination number would be 6. So how can you name the coordination number? You could say that coordination number is equal to denticity into number of ligands. So you need to know the denticity of all the ligands, my dear student. Okay. So coordination number is always equal to the denticity into the number of ligands used. Perfect. Let's move forward. Let's move forward. Next is your oxidation number of the central metal. Now you have to find the oxidation number of central metal. We'll use that one particular example which we have been using from the starting, which is K4FeCN6. Now, you have to calculate the oxidation number of the central metal. How are you going to calculate the oxidation number of the central metal? Ma'am, I know that central metal is this Fe, and my dear students, it is one of the most easy and one of the most important part of this chapter to calculate the oxidation number, right? Yes. So let us say that its oxidation number is X. Clear? Yes. You know that CN, cyanide, is a negatively charged ion. You need to remember the charges of all the ligands. The charges of ligands are to be remembered by you. That is the most important part. Okay, so if I talk about Cn minus, I would say that oxidation charge of Cn minus, that is minus 1. Yes, ma'am. Now, my dear students, just imagine. If you cross multiply it, can you say that it is actually K plus and this is Fe Cn whole 6 4 negative? This is how you actually write the compounds, right? You've learned in chemical bonding. You cross multiply their charges and you get this formula. Yes, perfect. I'll just tell you. You have K, you have Fe N whole 6. This is plus 1. This is minus 4. You cross multiply them. You get K4 Fe N 6. This is how you actually form a compound. Yes. So from here, you can find the charges of K plus and Fe4 Cn whole 6 4 minus. Now, my dear students, you know that we are saying that charge on the iron is X. I don't know what is its charge, but the overall charge of this would be 4 minus. Yes. So, ma'am, charge of Fe, which is X, plus 6 into charge of 1 Cn, which is minus 1, will give me 4 minus. Yes. Or I would say minus 4. Now, X minus 6 will give me minus 4. So, X will be equal to plus 2. So, the oxidation state of iron would be plus 2. This is how you are going to actually calculate the oxidation states of all the central metal, and it is very important to solve the numericals. Okay, so now let's see. Charge that the central atom should carry if all the ligands are removed along with the electron pairs that are shared with the central atom. Okay, let's move forward. What is next? Next is types of complexes. My dear students, there are two different types of complexes. What are the two different types of complexes? They are homoleptic complex or heteroleptic complex. What does this mean? If you have a complex, let us say FeCN whole 6. Here, if you see, all the ligands are same. Homo, that is all the ligands are same. When all the ligands are same, you can say when all the ligands are same, then we call it as homoleptic complex. What would be heteroleptic? I think you can guess now, right? Yes, ma'am. If you take Fe and you put Cn whole 4 and you put, let us say OH whole twice, what will this give you? This is a heteroleptic complex because you have two different types of ligands. So you'll write when ligands are different. When ligands are different. Clear? So this is how you classify them as homoleptic or heteroleptic. Perfect. No issues. Perfect. Let's move forward. Now we are going to do what is in Hindi it is called as Namkaran, but in English we are going to call it as nomenclature, right? Yes. So now we are going to name every compound, and this is the most interesting and amazing part. So now let's first learn what is the suffix that you are supposed to use for the ligands. If it is positively charged, negatively charged, you need to know the charges and you need to know their names, their suffixes which you are supposed to. First and the most important thing, all the anionic ligands, you will use O as the suffix, their name and then O, their name and then O, their name and then O. Let's move forward. If you have any halogen, you will call it as halido. If you have any halogen, you will call it as halido. This means that if you have fluorine, you will call it fluorido and its charges -1. If you have chlorine, you will call it chlorido, charges -1. Bromine, bromido, -1. Iodine, iodido, -1. Hydrogen, hydrido, -1. O2 minus oxido. O2 minus oxido. My dear students, you have to understand this. You have to, very, very important to understand this. O2 minus is oxido. Okay, O2 minus is oxido. If you have N3 minus, N charge is 3 minus, you call it nitrido. If you have N 3 and then charge is -1, you call it azido. Okay, Cn minus cyanido, my dear students, need to remember the charges. That is the most important part. Charge of cyanido is -1. Charge of nitrido is 3 minus. Charge of azide is -1. Azido, you name it. Nc would be isocyanido. And what can you say? We can say that, ma'am, these two are ambidentate. Hence, at one particular time, either cyanide or nitrogen. Now, my dear students, OH minus is known as hydroxide, do. NH2 minus is amido, and SCN minus is thiocyanato. NCS would be isothiocyanato. My dear students, these are ambidentate. Okay. NO2 minus nitrito N, ONO nitrito O. C2O4 2 minus would be oxalato. This is a didentate ligand. I'll just write it. Its structure. I'll write it here. Okay. What would be its structure? COO minus OOO minus. So its denticity is 2. Then you have CH3COO minus, you name it as acetato, right? Yes, perfect. This is how you are going to actually name all the ligands. Okay, there are a few in your NCRT. Just go through all the table and you'll understand it. Okay, that is important. You have to learn it. I am writing here, learn it. Okay, perfect. I'll move aside. You can take a screen. Now let's move forward. Go through the NCRT as well. If you talk about the cationic ligands, then you have NO plus, which is known as nitrosonium. It is known as nitrosonium, right? NO2 minus nitronium, NO2 plus nitronium. Okay, perfect. Let's move forward. Neutral ligands, you have water, which you will name as aqua, CO, carbonyl, PH3, phosphine, NH3, amine, and NO, amine. Okay, amine? No, NO is not this. Okay, NH3 is amine. Okay, perfect. Now let's move forward. You have a question and now you are going to answer the question. Okay, we'll practice and then you'll understand. Now. So the question is here. You have give the order of chelating effect of the following ligand. Now, my dear students, I am telling you what is EDTA. Ethylene diamine tetraacetic. Okay, now I am not going to give you a structure because EDTA is very, very important, and if I'll give you the structure, you will not learn it. So you have to find out the structure of EDTA. I'll give you a hint that its denticity is 6. Okay, what is diene? Diene's denticity is, my dear students, 3, and its structure should I give? Should I give its structure? I have actually given you its structure just a few slides before. Okay, its denticity is 3. That is important. Ma'am is telling you. Next is C2O4 2 minus. We just learned it, oxalato, and I told you that its denticity is 2. It has 2 donating sites. So I gave you the denticity of all the ligands, but your homework would be learning their structures. I am not giving you in your hand because I know then you will not go through their structures on your own. That is a human tendency. I know that. So you are going to go through their structures on your own, my dear students. It is very, very important to know the structures. Okay, so go through the structures. Denticity is given. Give the order of chelating effect of the following ligands. Okay, I am getting aside. Give the answer. Ma'am is drinking some water till then. Okay. You might have answered it till now. What will happen? And we know that if you are talking about the order of chelating effect, the more the number of chelate rings, the more would be the chelating effect, and the more the stable would be the complex. Okay. So we know that when you talk about the chelate rings, it is always equal to the denticity minus 1, right? Yes. So ma'am, in first case, we have denticity 2. So the chelate ring would be 2 minus 1, which is equal to 1. If I talk about the second case, the denticity is 6. So ma'am, the chelate rings would be 6 minus 1, which is equal to 5. If I talk about the diene part, ma'am, it has 3 denticity minus 1, so ma'am 2. The more the number of chelate rings, the more would be the stability, the more would be the chelation effect. So the first would be second, then third, and then first. Right? Yes. So which is the correct option? 2, 3, 1. Option C is your correct. So this is how you are going to solve the questions. Let's move forward. Let's move forward. Now we are going to talk about the nomenclature, right? Yes. So you need to know the rules as well. So rules are very simple. You just need to understand that how are you going to name it. I'll give you the perception in a layman language, and then we'll read the rules. The first is, you know that whenever you write a complex, you write the cationic part and then the anionic part. So you will name it accordingly. First, the cationic part would be named, and then your anionic part. Now, the coordination sphere could be your cationic part or it could be your anionic part. It depends. No problem. You have to name it accordingly. First. Second, my dear students, is the rule that I'll write the rule. I'll explain the rules first by myself, and then we'll rules. First, we have got it. Second is, you are supposed to calculate the oxidation number of the central metal, because in nomenclature, you actually write the oxidation number of the central metal. So calculation of oxidation number is important. After that, you are going to name the ligands alphabetically. Alphabetical order is most important. This means that if you have two ligands, let us say you have NH3 as a ligand and you have, let us say, chlorine as a ligand, then in the nomenclature, first amine will come and then chlorido. Okay, so this is very important that you name the ligands according to their alphabetical order. At the end, after writing all this, you will write the metal name and then its oxidation number. Okay, so first all the ligands will be there, then the metal name, and then its oxidation state. Now we know that ligands would be named according to their alphabetical order. Perfect. Next, ma'am. What if you have something like this? Let's say it is platinum. Okay, so something like this. Okay, let's. Now, how are you going to name this particular compound? You have to see that amine is first. Yes, it has 2 in front of it, that is 2 ligands are used. So you will write diamine. You will write diamine. Then you will write dichloro. The alphabets of di, tri, all these would never be considered. Okay, all these would never be considered. So diamine, dichloro, then platinum, and then, my dear students, you are going to write their oxidation state, whichever would be calculated. This is just an example, so I'm not writing its oxidation state. Whatever its oxidation state is, you will write it in Roman numbers. Okay. So the alphabetical order of di and tri, that is not considered. Only the ligand's name alphabetical order is actually considered. Okay, ma'am. Easy. First the cationic part, then the anionic part. Now what happens that sometimes you have, let us say you have bromine, something like this, you have Br2. Okay, now my dear students, this is your coordination sphere. This means that this is your cationic part and this is your anionic part. Yes, ma'am. So first you will name the cationic part, you will name this, which is diamine, dichloro, platinum, and then its oxidation state, and then you are going to write the anionic part. In anionic part, you're not going to write it as bromido because it is not acting as a ligand. It is not a ligand, it is an anion here. So when it is an anion, you will write as bromide. Its name would be bromide. But you will not consider this number. This number will not be considered. This number is only and only considered when it is in the form of ligands. If it is not in the form of ligands, it is a cation or an ion, then you are not supposed to write di-tri. No, you're not going to write that. You're only and only going to write the name of the anion, which is bromide. Okay? You're not going to write bromido as well because it is not acting as a. These are the basic rules. Okay? Now we are going to read all the rules one by one and I'm going to explain you as well. But first you know this, now you'll understand the rules even better. Now let's move forward. First, write the cationic part name, then the anionic part. Crystal clear, no issues. Generally, no requirement to write the number of cations or anions of ionization. I told you that we are 2 is not supposed to be written. If you have something K2 and this, then you don't have to write dipotassium. You only write it as potassium, because this 2 is not considered when they are cation or anion. These numbers are only considered in the coordination spheres. Perfect. Generally, no requirement to write the number of cation or anion of ionization spheres. Next, naming of coordination sphere. Now, how are you going to name this inside of the coordination sphere? You know the rules. Don't worry. You only have to revise. First, write the name of ligands. First, the name of ligands will come, then the metal, and then its oxidation state, according to their nature, positive, negative, or neutral, right? Yes, in alphabetical order. You know that alphabetical order with their number. If you have 2, you will use di. If you have 3, you will use tri, 4, tetra, 5, penta, 6, hexa, 7, hepta, and so on. No issues? Perfect. When the name of the ligand includes a numerical prefix, a very, very important thing, my dear students. If your ligand itself contains, let us say I am talking about ene. What is ene? Diethylamine. Diethylamine. Right? Yes. Ma'am, it's the ligand's name itself constitutes of di. So, if I have some complex, something like ene whole twice, what am I going to do? Will I write it as diethyl amine? Diethylamine? No, you're not going to write it like ethylene di. Oh, okay, wait. Ene is ethylene diamine. Sorry, my dear students, it is ethylene diamine. Yeah. So if you have ene, whose name is ethylene diamine, yes, ma'am. So am I going to write this as diethylene diamine, and then the metal name, and then the oxidation state? No, this is wrong. When you have organic names like ethylene diamine or diethylene triamine, which I gave you diene, the name I gave you, ligand diene, which is diethylene triamine, right? Yes. So, my dear students, since these are your organic names of the ligands, there you're not going to write di and tri. You're actually going to use these words. For 2, you are going to use bis. For 3, you are going to use tris. For 4, you are going to use tetrakis. 5 for pentakis. Right? Yes. This is how you are going to name them. So, ma'am, this means that how are we going to name MEN whole twice? We are going to name as bis ethylene diamine, bis ethylene diamine, and then the metal name, and then its oxidation state. So the compounds which itself contains di, tri words, or the compounds which are organically named, organic names are given to you, you are going to write bis, tris, tetrakis, pentakis, these forms of these names for their numbers. Okay, you have to understand this. You will develop this this thing with practice. Perfect. Let's move forward. I'll make you understand this as well. Don't worry. Name of the central metal or ion. Now you have 2 possibilities. Either your coordination sphere could be your cationic part, or it could be your anionic part. If it is your cationic part, then you are going to write the names of the metal as silver, gold, lead, tin, iron, platinum, the way they are named normally. But if your coordination sphere is in your anionic part, something like this. So this time the coordination sphere is your anionic part, and in that case the metal would be named as, for silver it would be argentate, for gold it would be orate, that is you use a word which is 8. For platinum it would be platinate, for chromium it would be chromate. This is how you are going to name the anionic part. Okay, yes, very good. So in the last, write oxidation number of coordination central atom in the Roman number in a bracket. I hope you understand that. Perfect. Let's move forward. The ligands are then listed in the alphabetical order. The placement of a ligand in the list does not depend on its charge. Polydentate ligands are also listed alphabetically. All the ligands are actually arranged in the alphabetical order. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. Clear? Yes, very good. Let's move forward. The formula of the entire coordination entity, the formula of the entire coordination entity, whether charged or not, is enclosed in a square bracket. Clear? No issues. There should be no space between the ligands and the metal within a coordination sphere. There would be no space. Don't worry, we will not write it, giving it. Clear? Yes, let's move forward. When the formula of a charged coordination entity is to be written without that of the counter ion, if you don't have an ion, the charge is indicated outside the coordinate square brackets as a right superscript with the number before the sign. This means that if you are not given it something like this is how we write a complex. Now, they are saying that suppose you are not writing this cationic part, you only have to write the anionic part. How are you going to write it? You will write it Fe, then Cn whole 6, and then 4 minus. That is, you have to write the number and the charge and the complete coordination sphere if you are not writing the cationic. Okay? Yes, that is, its charge should be shown. Its charge should be shown. Perfect. Next, the charge of the cations is balanced by the charge of the anions. Obviously, only then a complex is stable. Perfect. Let's move forward. Now we have to practice some, right? Yes, how are we going to name them? How are we going to practice the questions? So just here. Before this, I would like you to practice naming. Okay, so first we'll practice naming. Where are the compounds? Yeah. First try this question and then we will move forward. Okay, yes. So here are the questions. You have to practice. I'll move aside and try naming them and then we'll start. Okay, so now let's start. If we talk about the ligands, so first of all, we have, in the first case, we have AAC as a ligand. Is this ligand? If you will read your NCERT, you will actually get this ligand. So this actually is your ligand with this particular, right? Yes. So this is your acetyl acetonato. This is your acetyl acetonato. This is how you name it, acetyl acetonato. It has a negative charge. It has -1 charge. Okay? Yes. So how are you going to name it? First of all, ma'am, we have to name the ligands and then the metal, right? There is no cation or anion sort of a thing. So we only have to name the coordination sphere. So first we are going to name the ligands. I told you that if you have organic names like acetyl acetonato, right? So it is an organic name. So if you have some number before it, you're going to name it as bis, tris, tetrakis kind of. Yes, so here is 3. So we will say tris acetyl acetonato. Acetyl, tris acetyl acetonato. You have the central metal as chromium, and since it is not an anion, we will name it as chromium only. So this would be chromium. And now you are supposed to calculate its charge, my dear students, which will come in its Roman number, right? Yes. So now let's calculate the charge. This is X, right? Now you know that charge on one acetyl acetonato is -1. This means that, ma'am, X plus 3 into -1 is actually equal to 0. There is no charge on this particular coordination sphere. Yes. So this means that X would be equal to +3. So the charge on the central metal is 3. So here it will come in Roman numbers as 3. Right? Yes. So tris acetyl acetonato chromium. Perfect. 3. This will be your correct answer. Let's move forward to the second part, which is your B part. B is, you have vanadium as your central metal, then you have H2O, which is 6, and then you have chloride as 3. And now, my dear students, how are we going to do this? First and the most important thing is we are going to name the cationic part first. So you have the cationic part here. Yes, ma'am. First, we are going to name the ligands. So let's name the ligands. You have only one type of ligand, homoleptic. It is a homoleptic complex. You have H2O as your ligand, and it is a neutral ligand. Charge on H2O is 0. You have to learn it. I told you. Now, my dear students, if you talk about this, you have a 6 as the number for the ligands, and it is not an organic name. So, you can write it as hexa. Yes. So, hexa, the suffix for H2O is aqua. So, hexa, aqua. Then, what is the metal? Vanadium. Since it is in cationic part, so we'll write it as vanadium only. We have to calculate its charge. And then, my dear students, chlorine is not actually your ligand here. It is the anion here. And for anion, we don't write their numbers. And we only write their name as chloride. As chloride. Not chlorido. It will be named as only chloride. Okay? Yes. So, hexa aqua vanadium chloride. Perfect. Now, let's name this particular part. Now, how are we going to calculate the charge? See, we'll again consider it as X charge. Yes. See, my dear students, if you are taking Cl3, this means that here the charge is plus 3. I hope you understand this concept, that cross multiplication concept. So, ma'am, X plus 6 into charge of 1 H2O ligand. It is a neutral ligand. So, ma'am, charge would be 0. This will be equal to plus 3. So, this means that charge on the vanadium is plus 3. So, here you will write 3 in Roman numbers. So, this would be the name for this particular complex. Right? Let's move forward. C part, my dear students. C is NH4 whole thrice. You have NH4 whole thrice. Then you have CO C2O4 3. Okay. CO C2O4 3. Right? Yes. Is there any charge? No. Okay, perfect. Now, if you have 3 here, can you understand that this means that this is negative of 3? Charge is negative of 3. I hope you understand this. Yes. Now, since this is your cationic part, so you will write its name normally. Yes, ma'am, you will not consider this 3 here. So you will write ammonium. You will write ammonium. Then after ammonium, now you're going to name it as in your anionic part. In anionic part, ligand's name. Yes, ma'am. Now, my dear students, you have to understand that C2O4 is actually your oxalato. See, I'll give you the structure as well. COO minus, COO minus. Right? Yes. So, the charge on oxalate is minus 2. Right? Charge on oxalate is minus 2 and you call it as oxalato. So, you are going to say tris because it is an organic name. So, tris oxalato. Tris oxalato. Tris oxalato cobalt. Now, my dear students, this is the most important part. Will you name it as cobalt or you will name it as cobaltate? Since it is in your anionic part, you will name it as cobaltate. 8 word would come. So, ma'am, cobaltate and the charge. Now, let's calculate the charge. If this is X, then ma'am, X plus 3 into charge of C2O4 is minus 2. This would be equal to minus 3. So, charge on X would be plus 3. So, ma'am, this would be 3 again. Right? This is coincidentally that every time the charge is coming 3. It can be 4, 2, anything, my dear students. So, don't make this assumption that every time the charge would be 3. Okay? Perfect. So, ammonium tris oxalato cobaltate 3 would be your correct answer. If you got the 3 correct, then this part is going to be your homework. This part is going to be your homework and you have to write the answer in the comment section. Definitely check. Okay? Yes. Let's move forward. Now, you are supposed to give me, I think, this question. Write the structure. Yes. Perfect. You have understood how to name a particular coordination compound. If you are given a name, how are you going to write the complex? That is the most important part. So now we are going to practice this question. Okay. Now see the question and try yourself. I will get aside. Okay. So let's start. The first is write the structural formula the corresponding to each of the following IUPAC names. Okay. The first is potassium. First part. Potassium tetracyanide zincate 2. See, if you can see that cationic part is potassium. So ma'am, this means that potassium is written normally. So first cationic part does not have a coordination. We'll write potassium. Then you are given tetracyanide. This means that the ligand CN would be 4 times, right? Tetracyanide, which is CN. So tetracyanide, and then you have zincate. This means that in the anionic part, the central metal is zinc. Okay, yes, and you are given the charge to be 2. So the charge of your metal is plus 2. So you have to calculate the total charge here so that you can give potassium a number. Okay, so now how are we going to do this? See, my dear students, I know that zinc charges plus 2, and I know that CN is a ligand, negatively charged ligand. It has a charge of minus 1. So this means that ma'am, plus 4 into minus 1. This will give you the value as plus 2 minus 4, which is equal to minus 2. Right? So the total charge here would be minus 2. If its charge is minus 2 and this is plus 1, cross multiply them. What will you get? You will get K2 Zn CN4. This would be the formula of your coordination complex, right? Yes. Now, can I ask you what is the coordination number of this particular compound? What is the coordination? Ma'am, if I see, then CN is a monodentate ligand. It will form only one coordinate. And since there are 4 ligands used, so the coordination number is 4. So coordination. This is how you are going to find out, right? You are supposed to answer like this. Now let's move forward to the second part, which is P. P is tetracarbonyl. Tetracarbonyl means that this time the coordination sphere is your cationic part, because we name cationic part first and the ligands are given in the cationic part. This means that it is a cationic ligand. So ma'am, I'll write as carbonyl, CO, and it is tetra. This means 4. Tetracarbonyl, and then you are given nickel. So ma'am, nickel, and there is no charge for nickel given, right? Yes. This means that nickel charge is 0. Okay. So how are we going to calculate the total charge on this complex? Let's see. The charge on nickel is 0, plus you have carbonyl 4 into what would be the charge for carbonyl CO, my dear students? The charge on carbonyl would be, ma'am, 0. It is a neutral ligand. We have learnt this as well. So the total charge on the complex would be, my dear students, 0. So here no charge will come, or you can write 0. It's one and the same thing, right? Perfect. So B part we have written. Now let's see the third part, because fourth part is going to be your homework as usual, right? Now let's see the third part. Potassium tetra. Potassium, again, my dear students, this time also cationic part does not contain the coordination sphere. So ma'am, potassium. Then I have tetracyano. Tetracyano, this means that CN4. Tetracyano, nickelate. Then this time you have nickel, my dear students, and its charge is 0. This means that, ma'am, 0 plus 4 into minus 1 will give me how much? Minus 4, right? Yes. So this is minus 4 charge. So here it will be minus 4. So you can write as K4 NiCN whole 4. This is how you are going to name the third part as well, right? Yes. So this is your homework. Again, D part will be your homework. You are supposed as well, right? Yes, perfect. So I hope you got the nomenclature. How are you going to do the questions? Let's move forward. So now let's do the next question. Now, here is the question. Now you have to answer the question. What does this question say? The IUPAC nomenclature for the complex, this is. Now you have to give the name. Okay, you can just cancel out the options. It is very easy. How are we going to do? First, you have to do yourself. Pause the video and then you. If I see, then first, ma'am, it is sodium. It is the cationic part. The sphere is in the anionic part, right? So the metal name should contain 8 words. This is something I know from very starting. So ma'am, first name should be sodium. So yeah, all the options have sodium. The second thing is that the metal's name should have what? 8 word in it, right? Yes, ma'am. So 8 is here, it's here, ma'am, but not here. So this would be not correct. This would not be correct. So you are left with only two options. So 50-50 has been done, right? Yes. Now let's find out what other things we can find out. Ma'am, sodium, then this is calculated, no issues. If I see the oxidation number, you have 2 as the oxidation number. This means that you are not supposed to even calculate the oxidation state. It is 2. It is known to you. Okay, you don't have to calculate it. You only have to name it. Let's name it. First, we have bromido, we have chlorido, we have nitrito, N, and we have amine. So, no, according to the alphabetical order, amine should come first. So, sodium, 1 amine, then it should be bromo. So, this would be amine, and here it is written nitro. Nitro cannot come in alphabetical order before amine, right? So, this is also wrong. You are here with the correct answer. Not even naming it on your own. You just cancelled out the wrong options. This is so easy. Sodium, then my dear students, amine, then bromido, then chlorido, then nitrito, N, because this time the linkage is from N, and then you're done, right? So sodium, amine, bromo or chloro. See, in the previous time, when now you name it as chlorido and bromido, but initially you used to name them as bromo and chloro as well. So don't get confused. It's okay if you are writing it as bromido and chlorido. That is also correct, but the rules have just changed a few years back. So initially it is a previous year question. So the options are given bromo and chloro. So don't get confused. Okay. Yes. So sodium, amine, bromo or bromido, chloro or chlorido, nitro N or nitrito N is absolutely correct. Again, my dear students, sorry, but this is what happens when the rules get changed. So you can name it as nitro N or you can name it as nitrito N. It's one and the same thing, platinate 2, right? Yes. So option C is your correct answer. So here a few things which I think I should tell you. Initially, bromine used to be called as bromo, but now since the rules have changed, you can call it as bromide. Initially, when you were naming NO, it used to be called as nitro N, but now you call it as nitrito N. Okay, no issues? Perfect. Now let's move forward. Next question, my dear students. Now you have to answer this question. Okay. So the question says the correct name for the complex ion this is. Okay. So for this complex, how are you going to name it? The first and the most important thing is you don't have a anion. You don't have a cationic part. It is actually an ion. So ion word should be there at last. So ion, ion, ion. Absolutely right. Since the oxidation state is 3, so you're not supposed to calculate the oxidation state. It will come out to 3. Now, ma'am, since it is in the cationic part, so 8 word will not be there for the metal. So first, let's see if there is written as 8 somewhere. Yes, ma'am, it is written cobaltate. So this is not the correct option. Others are, I think, fine. No, here also cobaltate. So this cannot be correct. Okay, so 2 options again gone. Let's see what would be the answer. If I see, I have chloro, I have nitrito O. This times the linkage is from oxygen side, so it is nitrito O. So chlorido or chloro, what is it? What it is written? Chloro. Okay then. Chloro or chlorido, one and the same things. So chloro, nitrito O, and this is ethylene diamine, my dear students, which will be known as bis-ethylene diamine. Okay, yes ma'am. What will come first? Chlorine, alphabetically chlorine first, and then ethylene diamine, bis-ethylene diamine. So let's see, chloro, then I should have bis-ethylene diamine. So chloro, bis-ethylene diamine, then nitrito O, cobalt 3 ion. So ma'am, option D will be my correct answer, right? Yes. So in this case, option D will be your correct answer. This is how you are going to find out the correct. It's interesting, right? Yes. Let's move forward. Let's move forward. Now, my dear students, the next part which we are going to discuss is the Werner's. What is Werner's theory? My dear students, Werner actually gave you that there are 2 different types of valencies in a coordination number. It has primary valency and it has a secondary valency. One of the valency is ionizable and the other is not ionizable. What does this mean? We are going to understand. Okay. According to this, metal cation in complex compound has two types of valency. It has two particular type of valencies. The first is the primary valency, which is your oxidation number, and it is ionizable. And the other is your secondary valency, which is your coordination number, and it is non-ionizable. Okay, so primary valency is ionizable valency. I told you primary valency is your ionizable valency, whereas the secondary valency is your non-ionizable valency. Every metal cation in complex compound has a fixed secondary valency. What does this mean? Ma'am, please explain. I am here, why to fair? Right? Let's start and understand. The only example we are using till now, which is F, E, C, N, 6, A, 4. Right? Now, first write the central metal, F. Werner's theory told you that it has two types of it. Primary valency, which is ionizable, and the secondary valency, which is non-ionizable. Right? And secondary valency is actually the coordination number or the coordination bond wala part. Right? Yes. So you can say that you have Cn in the sphere, right? That would be your secondary valency. So you will have Cn here, 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 and Cn. This is your coordination compound, and this is the secondary valency, which is inside the coordination sphere, and it is non-ionizable. These ions will not get dissociated, and you know that whenever you dissociate this, K4 will go this side, but this particular sphere will keep intact. This means that secondary valency is non-ionizable. The ligands which form coordination bond, they do not break on adding into the aqueous solution. If you talk about the potassium part, I can say that potassium part would be something here. Potassium part would be here. Potassium part here. And potassium part would be right here. So you see that the dotted part is your primary valency. And the blue part, which is the straight line, is your secondary valency. What can we say that from here? That primary valency is ionizable. Whenever I'll add this into the aqueous solution, I'll get 4K plus and Fe n 6 intact. Right? Yes, ma'am. This means that the primary valency is ionizable, but the secondary valency is non-ionizable. If I talk about the directions or the orientation, what can you say? Since the secondary valency is forming a particular coordinate bond in a particular part, it is directional. Whereas if you talk about the ionizable part, it is non-directional. It could be anywhere, right? Yes. So this is how Werner classified it. Primary valency, oxidation number. I hope you got it. Secondary valency is the coordination. This is understood. Let's move forward. Okay, now we have to do, right? So let's do some questions, my students. The question is, the coordination number of a central metal in a complex is determined by. How are you going to calculate the coordination number of a central metal atom? Right? Yes. So we see that the number of only anionic ligands, is it only anionic ligands? No, ma'am. It could be positively charged ligands as well or neutral ligands, right? So that is a wrong option. Perfect. Next, the number of monodentate ligands around a metal ion bonded by pi bonds. Whenever you talk about the coordinate bond, it is never a pi bond. It is always a sigma bond. It is always a sigma bond, not a pi bond. So this is wrong. Next, the number of monodentate ligands around a metal ion bonded by sigma and pi bonds. No, my dear students, only and only sigma bonds. We never talked about the pi bond, right? Yes. So this is again a wrong option. Fourth option, the number of monodentate ligands around a metal ion bonded by sigma bonds, which are the coordinate bonds. Yes, ma'am. So option D will be your correct answer. This is how you are going to do the question, right? Yes. Perfect. You can understand this. Then we will move forward. Let's move forward. Now, Now, I just told you that primary valency does not have a directional nature, but your secondary valency has a directional nature. So now we are going to understand. Okay. Yes. So here is your primary valency. Non-directional. And you have your secondary valency direction. Perfect. No issues. Now, what we are going to understand is very, very important. You are given some ions. You are given some ions. Let us say you have COCl3 dot 6NH3 and you are given AgNO3 in excess. Okay. This is your first part. Let's say what is your second part. In second part, you have COCl3 dot 5NH2 plus AgNO3 again in excess. Okay. Let's say third part. Third is you have COCl3 dot 4NH2 plus AgNO3 in excess. Right? What does all this tells us? We'll just understand this. Just a second. Okay, so now let's start. Now, if we talk about this, you have COCl3 and 6NH3. You have COCl3 and 6NH3. Just a second. Just a second. NH. We are going to write ammonia. Yeah. So now, if you see that you have COCl3 dot 6NH3, which is going to react with AgNO3 in excess, and this is a aqueous solution. This will also be a aqueous solution. This will also be a aqueous solution. So now, how are you going to tackle these type of questions? I am going to make you understand this. Now, my dear students, if you see, you have AgNO3 in excess, and always remember what you have learnt in your halogen part, in your inorganic group 17, what you have studied, that when AgNO3 reacts with the Cl minus, you actually get AgCl as PPT. Whenever AgNO3 reacts with the Cl minus ion, you get AgCl as your PPT. Okay, yes. So here if I see that there will be the formation of a complex compound. I told you that when two different types of salts are mixed, either they form a double salt or a complex compound. Here you will get a complex compound. What complex compound you will get? You will get CO, you will get NH3, and that is total 6 ligands. So you will write it here 6, and plus what will you get? You will get AgCl. How many AgCl? 3 moles of AgCl. You will get 3 moles of AgCl. So here I can say that I got 3 moles of AgCl. Right? Perfect. Now let's think about this part. Here if you see that you have AgNO3 in excess, no issues, perfectly fine. If you talk about this particular part, again you will get a complex, right? This time you will get a CO. But here, what you can see is that you have amine ligands only 5. This means that 5 ligands would be here, which is NH3, 5. But still, one coordinate bond is yet to be made. And since you have amine ligand, only 5 ligands are available. So you have written 5 here. You need one more monodentate ligand. So here you will use one of the Cl from the COCl3 part. This means that one Cl will act as a ligand. One Cl will act as a ligand, and the next other part would form the PPT. That is, now you are left only and only with 2 moles of Cl. So you will get 2 AgCl, that you will get 2 moles of AgL. right? Now let's move forward to the other part. If we talk about this particular reaction, we see that we have COCl3.4NH3. This means that, ma'am, I will get O, I will get CO, and then I have 4 NH3 ligands, so I'll get NH3 amine 4. And if I see, still two coordinate bonds are yet to be made to form the coordination number as 6. If I see, then 2 Cl will act as ligands and I'll get Cl2 here, and I will only get 1 mole of AgCl. So you hear only 1 mole of AgCl is formed. Okay. So this is how you understand everything about it. If I talk here, you can see that the directional, that is your secondary valency, in all the cases is 6. Right? Similarly, you can calculate the primary valency also by calculating the oxidation number. Right? Yes, perfect. Let's move forward. You have a question, you have to answer this question. What does this question say? A complex of ammonia and chlorine. You have a complex of ammonia and chlorine. See, ammonia NH3, right? A complex of ammonia and chlorine produces 4 ions. This is not SOR, my dear students. This is 4. Okay. Perfect. So, a complex of ammonia and chlorine produces 4 ions. It will produce total of the 4 ions per molecule in the solution. Now, you have to consider all the complexes, then dissociate them into their individual ions and calculate the total number of ions you get. The complex which will give 4 ions is your correct answer. So now let's see. If I talk about this particular thing, I'll get 3 Cl minus ions and 1 complex. Yes, ma'am. So total I have how many? 4 ions. Clear? Yes. Let's talk about this particular part. If I see here, I'll get 4 Cl minus ions because I have Cl4 here and this particular whole complex. So I will have total of 5 ions here. If I talk about this particular part, I'll only get 1 ion. I'll only and only get 1 ion, which is my coordination sphere. It will not get dissociated. If I talk about the D part, what will I get? I will get 1 coordination sphere and 2 Cl minus ions. So total of 3 ions I'll get here. I want 4 ions. Which is the case where I can get 4 ions, ma'am? Option A. So my dear student, option A will be your correct answer. Right? Yes. So option A is your correct answer. Very good. Let's move forward. Next question, my dear students. Next question is here. Now you have to talk about this question. Read the question, pause the video and try yourself. The question says a 6 coordinate complex of the formula, you have been given a formula, has green color. Okay. A 0.1 molar solution of the complex when treated with excess of AgNO3 give 28.7 grams of white PPT. White PPT is because of the formation of AgCl. I am telling you this. The formula of the complex would be. Okay, pause the video and try to do this question and then I'll make you understand the question. Let's do this question now. What will happen? First and the most important thing is mass of AgC. Mass of Ag. Molar mass would be 143 grams. Approx 143. Right? Yes. Now, my dear students, it is said that the complex is 0.1 molar. You have 0.1 molar of this particular complex, which actually includes your coordination sphere and the ions as well. Okay, so I have this as 0.1 molar. I don't know how many Cls are outside, so I'll write Cl3.6H2O. Okay. Now, when this reacts with AgNO3, I get some moles of Ag plus the complex. Now, my dear student, I very well know that the moles which I will get of AgCl will be exactly equal to the moles of Cl ions which act as your anion. Right? Yes, which will act as your anion? This number? Yes. So I can say that if I calculate the moles of AgCl, they will be equal to the moles of Cl as anion, right? Yes. Since this is 0.1 mole, so this should be in some 0 point form, right? So now let's calculate the moles of AgCl. So if I calculate the moles of AgCl, what will I get? Moles of AgCl, my dear students, 28.7 is the given mass, 28.7 divided by 28.07 divided by 143, 28.7 divided by 143. So this would be into 1 upon 10, this would be 1 2, so this will be 0.2. So basically you have got 0.2 moles of AgCl, right? Yes. So what can I say? That 0.1 mole of this complex is giving you 0.2 moles of AgCl. This means that two chlorine ions, this means that two chlorine ions were actually present outside the sphere. This means that this N value is 2. I hope you understand that if it's 1 mole is there, you will get 2 moles here. If it has 2 moles, you will get 4 moles. It has 0.1 mole, it is giving you 0.2 moles. This means that how many moles of Cl were outside? It was 0. It were 2 number of chlorine ions which were outside the coordination sphere. So if I can say that N value is equal to 2. I just calculated it. If N value is 2, this means that outside the coordination sphere, I have 2 chlorine ions. What am I left with? You have chromium. Now you want 6. You want what? You actually want, my dear students, 6 H2O, right? You have 2 chlorine outside. So, my dear students, you will have 1 chlorine inside as well. Yes, ma'am. So, 1 chlorine I will have. Rest of the 5 ligands would be water. So, you will have H2O 5. Now you are still left with 1 H2O, right? Yes, then that H2O would be somewhere. So this is how you are going to find out the correct complex. Let's see which is the correct answer. Chromium, then you will have 1 chlorine inside, then you will have 5 H2O, then you will have Cl2. Okay, my dear students, there is a little correction. It is Cl2. Okay, dot H2O. So option B will be your correct answer. So what I did, I calculated how many moles of AgCl I am given. I calculated the moles of AgCl. I could find out that how many Cls were free. They could be ionized. 2 Cls could be ionized. This means that 1 out of these 3, 2 Cls are here. This means that 1 Cl would be inside. Yes, ma'am. So I wrote 1 Cl inside. Then, how many H2O ligands do you have? You have 6. But inside the coordination sphere, the coordination number is 6. This means that only 5 H2O could be there. So, 5 H2O you've written here. So, 1 H2O has to come out, which is H2O. So, this is how you are going to calculate, find out your coordination complex. Let's move forward. Okay. So, can I give you this as your homework? Can I give this question to you as your homework? So, my dear students, this would be your homework again. Which statement about the coordination number of a cation is true? Okay, so this is very simple. You have to do this question on your own. Okay, let's move forward. Next question. No, next theory. So now we have discussed about the Werner's theory. Now we are going to talk about the valence bond theory, and this is the most important theory. Most of the questions are asked from this particular theory. What does this theory say? There are attractions between metal and ligands. What does Werner theory say? Werner theory actually tells you that there are attractions, that is, there would be overlapping of the orbitals, right? Yes, I will make you understand each and every part slowly and slowly. Metal to ligand overlapping will take place. This means that you have a metal, it has an orbital, the ligand will come, it will donate its electron, and they will overlap, and you will get a bond like. Okay, so central metal atom or central metal ion attracts to the ligand. Clear? Ligand provides the lone pairs to the central metal atom or central metal ion, and they provide vacant orbitals for these lone pair of electrons. Next, my dear students, pure vacant orbitals of the central metal atom or ion equate their energy by intermixing of their orbitals. This is known as hybridization. What does this mean? That is something that I will make you explain. Okay. Ligands form coordinate bonds. I told you they form coordinate bonds by overlapping with an empty hybrid orbital, right? Empty hybrid orbital of the central metal atom or ion. Type of hybridization, geometry, and magnetic moment of the complex compounds depends upon the nature of the ligands. This is the most important part from where the questions have been asked. You have to tell the geometry of your complex, you have to tell the magnetic moment of the complex, everything. So we are going to understand how are we going to calculate all this, right? So let's move forward. This is something which we will talk about in CFT. This is something which we will talk about in the next theory. So just leave it for now. Now, WFL means your weak field ligands. WFL means weak field ligands, that is the ligands which are weak. SFL stands for the strong field ligands which are strong. Okay, generally, my dear students, the carbon or nitrogen containing ligands, the ligands which have carbon and nitrogen in them, they are considered to be strong, and all your halogens are actually considered to be the weak ligands. Okay, yes. Do not affect the configuration of central metal ion. There is no pairing that would take place in the case of weak ligands, and in the case of strong ligands, pairing would take place. If complex compound has 0 unpaired electron, then it is known as a diamagnetic. We will calculate the number of electrons. If the number of electrons, if all the electrons are paired in the orbitals, as you know that in an orbital only maximum 2 electrons can take place. So if all the electrons are paired, it is a diamagnetic complex. If all the electrons are not paired, 1 or 2 are unpaired, then that is known as a paramagnetic complex. Right? Yes. The paramagnetic are actually weakly attracted. I hope you've studied this in the solid state chapter. Right? Yes. If you've not studied this, no issues. We'll discuss about this as well. Right? Yes. And this is how you calculate the magnetic moment, root n into n plus 2, where, my dear students, n stands for the number of unpaired electrons. Don't worry, it is too much of information to collect right now, but I'll make you understand each and every point one by one. Okay, so let's move forward. When inner shell, I'll make you understand everything with an example. Okay, if I'll give you an example, you will better understand it. This is important, my dear students. sp3, dsp2, sp3, d2, and d2, sp3. Okay, just a second. Okay, perfect. I hope it's not a problem now. I'll make you understand everything with an example. Now, how are we going to understand this? Okay, you have a complex. Okay, just understand you don't know anything about valence bond theory right now. There are a few steps which you have to follow, and you will be able to answer every question, and you will be able to understand every concept. You have a complex? Yes, ma'am. I know this is central metal. These are ligands. And ma'am, you told me something that ligands are strong and weak. The strong ligands actually pair the electrons, and the weak ligands don't pair the electrons. Okay. The strong ligands generally are the ones which have nitrogen present in them or carbon present in them, and the halogen ligands are actually the weak ligands. Okay, this is something which you need to know till now, and you know this. Perfect. Now let's move forward, my dear students. First and the most important thing for you is to calculate the oxidation state of the central metal. So first is step 1. What does step 1 say? Calculate oxidation state. What are you going to do? You have to calculate the oxidation state of central metal. Okay. Okay, ma'am. Let's calculate. We know how to calculate it. Yes, ma'am. This is hexaamine, and ma'am, amine is a neutral ligand. Its oxidation state is 0. I have no issues till here. Now, first and the most important thing is your central metal is cobalt. My dear students, let's calculate the oxidation state. Let us say the oxidation state of this is X. So, X plus 6 into 0 will be equal to plus 3. So, X is equal to plus 3. So, the oxidation state of CO is plus 3. Okay, now the second step would be write the electronic configuration. So you have to write electronic configuration of central metal. You have to write the electronic configuration of the central metal. Now, let's write cobalt. Now, remember, I told you, you need to remember the first 3 elements oxidation numbers. Okay, so scandium, titanium, vanadium, chromium, manganese, iron, cobalt, that is 27. Always remember the atomic number for cobalt is 27. So how are you going to write its electronic configuration? This would be argon. This would be argon 4s2. Then you have how many electrons left? You have till here we have written 18, 20, now 7. So ma'am, this would be 3d7. So this is your electronic configuration. I'll write argon, then 4s2, 3d7. Okay. Now this is cobalt, but you need cobalt 3 plus, right? So now you are going to write cobalt 3 plus. Cobalt 3 plus electronic configuration would be argon. When the electrons are left, they are loose. The electrons are lost first from the valence shell. Here the valence shell is 4. So first 2 electrons will go from 4s. Then you will get this as 4s0 and this would be 3. One more electron from here. So you will get 3d6. Okay. So we can say that this is something like this. I hope you get the point. Perfect. Now, can we fill the electrons? Yes, ma'am. You have 6 electrons. 4s is vacant. So 4s is vacant and you have 6 electrons. So 1, 2, 3, 4, 5 and 6 electrons are here. Right? Now, what will happen, my dear, is that you have a strong field ligand. You have a strong field ligand. So pairing will take place. So you will say that pairing will take place. Pairing takes place. So pair the electrons. What will you do? You'll pair the electrons. Okay. So pair the electrons, my dear students. What will happen? Let's write cobalt 3 plus. I can write 3D first and then 4s. There is no issue. So this is 4s. 1, 2, 3, 4, 5 and this is 3D. Okay. You will pair the electrons. This means that this electron will come here. This will come here. Right. So first 3 will be completely filled. So ma'am, first 3 would be completely filled. Okay. Perfect. Now my dear students, this is 4s and somewhere here you will have 4p as well. Right. Yes. Now, what can you hear? What can you see here, my dear students? That these 2 d orbitals are vacant. This s orbital is vacant and these 4p3 orbitals are also vacant. Right? Yes. So what are you going to do? These vacant orbitals will intermix. They will intermix. And when they intermix, what does this mean? By intermixing, all the orbitals form one energy orbitals. This means that all these orbitals energy would be same and this process is known as hybridization. When different energy orbitals intermix to form equal energies for them, that particular process is known as hybridization. So all these orbitals will hybridize. All these orbitals will hybridize. So I can write it as hybridize. Okay? And they will form degenerate orbitals. What are degenerate orbitals? The orbitals which have equal energies. So all these will have equal energies. So 2, then 1, then 3. So 1, 2 and 3. Right? So what can I say? What is the intermixing that is taking place? Ma'am, you have 2 d orbitals. So d2 and then 1 s orbital and 3 d orbitals, p orbitals. So here, my dear students, this is d2sp3. This is d2sp3. Hybridization took place and you saw that you are getting d2sp3 intermixing, right? Yes. When you get d2sp3 intermixing, now I think you can understand D2sp3 is a inner orbital complex. It is the geometry is octahedral and the bond angles are these. So you find out, you intermix the orbitals and you find out is it D2sp3 or sp3d2. Accordingly, it will be an inner orbital complex because the inner d orbitals are getting used. Because the inner d orbitals are getting used, so you will say that it is the inner orbital complex. Geometry is octahedral, right? So here I can write that geometry is octahedral. It will be octahedral if the coordination number is 6. So it is octahedral because the coordination number was 6. It is a inner orbital complex. Why inner orbital complex? Because the inner d orbitals were used, right? So because the inner d orbitals were used, that is the reason we are saying it is an inner orbital complex. Now, my dear students, since now, can you say that it is diamagnetic or paramagnetic? What is diamagnetic? When all the electrons are paired, and when all the electrons are not paired, we call them as paramagnetic. Since all the electrons are paired, so ma'am, I can say it is diamagnetic. And you are supposed to calculate the dipole moment, and I told you that dipole moment is calculated as root n into n plus 2. What is root n? What is n value? Number of unpaired electrons. How many unpaired electrons do you have? 0. So here the dipole moment would be 0, right? Easy? Yes. So this is how you will only and only calculate one thing, which is the intermixing. You will do this and you can understand all the concepts yourself, right? Yes. So this is how we solve the questions. I hope you got it. Perfect, my dear students. Now let's move forward to the next question. Try to do the question yourself and then I'll solve the question. So now let's move forward. Here is a next question. How are you going to calculate? Okay, let's see. You have a central metal again, which is again cobalt. So I have given you everything. So you can, I think, calculate everything, my dear students. First of all, ma'am, step 1 would be oxidation state. Okay, how are you going to calculate the oxidation state? X plus fluorine, my dear students. Fluorine, when is used as a ligand, it is F minus, so charge is -1. So ma'am, plus 6 into -1 is equal to -3. So X would be equal to +3. So the oxidation state is +3. So now I have to write the electronic configuration. So ma'am, for step 2, I can say that cobalt is 27. We've done this. Cobalt was 27. Yes, ma'am. So cobalt would be argon, 4s2, 3d7. Right? No issues? Perfect. Now, ma'am, cobalt plus 3 would be argon, 4s0, 3d6. Perfect. No issues. Perfect. Now, what I have to do? I have to intermix. So first, I'll write the d orbitals. And then I'll write 4s. So this is 3d. This is 4s. Clear? Yeah. You have 6 electrons in 3d. So 1, 2, 3, 4, 5 and 6. No issues. 4s is empty. Now, my dear students, you have to see whether you have a strong field ligand or a weak field ligand. You have a halogen as a ligand. Halogens are weak field ligands and they do not pair the electrons. So they will not pair the electrons. Yes, ma'am. So what you will have to do is you will have to write it. Next page, step 3. Step 3 is argon, 3d6, 4s0. So I'll write d orbital 1, 2, 3, 4, 5. Then I'll write 4s. Then I'll write 4p. Right? Then you will have d orbitals for 5d. Okay? Then you will get 5d orbitals. Okay? Sorry, 4d orbitals. Clear? Now, my dear students, what are you going to understand here? That you have this 3d, this is 4s, this is 4p, and this is 4d. 1, 2, 3, 4 and 5. Clear? Now, my dear students, what are you going to understand this? You have how many electrons here? You have 6 electrons. So ma'am, 1, 2, 3, 4, 5 and 6. No pairing will take place because I have a weak field ligand. Yes. So these orbitals are not free. I cannot intermix them. So you will have to intermix these orbitals. You will have to intermix these orbitals and you will have to form 6 hybrid orbitals. So now on hybridization, here hybridization will take place. Intermixing. Yes, and you will get what? 1 s orbital, then 3 p orbitals. So till now you got 4 orbitals, but you need 2 more. So the 2 more would be from the d orbital. Yes, ma'am. So 1 and 2. Clear? I hope it's clear. Perfect. Now, my dear students, you have 1, 2, 3, 4, 5, 6. What is happening? What is the intermixing that you did? You took S, you took S, you took 3 p orbitals, and you took 2 d orbitals. So sp3d2. This is what you have intermixed. This is what you have intermixed, right? Yes. So from here, what can you say? sp3d2. My dear students, geometry is still octahedral. I told you that if the coordination number is 6, the geometry would be octahedral. This time, the d orbitals which are going to be used are from the outside. These are not the inner orbital complex. It would form a outer orbital complex. So you will get a outer orbital complex. Now tell me, will you get, what will you get? Will you get a paramagnetic complex or a diamagnetic? Ma'am, I have unpaired of electrons present, so I will get a paramagnetic complex. So it would be a paramagnetic complex, right? And if I calculate the dipole moment, then root n into n plus 2. What is the value of n here? How many number of unpaired electrons? 1, 2, 3, 4. 4 unpaired electrons. So you have to put the value of n to be 4 and calculate the dipole moment. This is how you study the complex. Now these empty orbitals, in these empty orbitals, the 6 F ligands will donate their electrons and form coordinate bond. These are the vacant d orbitals which we were talking about in the complex. So here F minus will give electron, F minus, F minus, F minus, here also F minus, and here also F, right? And if we talk about the previous complex, I think I have not written here. What was the ligand? NH3. So here, my dear students, where should I write? I'll write with green color. NH3 will donate, NH3 will donate, here also NH3, here also NH3. I've made 7, what? 1, 2, 3, 4, 5, 6. I think I've made one extra. NH3 and H. Okay. This is how you are going to intermix the orbitals. You will make them degenerate and the ligands will provide their electrons in the vacant d orbitals. You can calculate all the information about the complex, right? So I think now you can understand everything. If you have octahedral geometry, you will have outer orbital complex or you will have inner orbital complex, right? It will have octahedral geometry every time. Tetrahedral geometry, square planar geometry, sp3 and dsp2 intermixing. Okay, this is how you're going to calculate everything, right? I hope you are clear with this concept. Okay, if you will read this theory now, you will understand everything. Perfect. Let's move forward, my dear students. This particular complex will be your homework. I'll tell you, carbonyl is whenever you talk about carbonyl, it is a strong field ligand with nickel 2 plus ion, right? And here you have to calculate the charge and which orbital is it, outer, inner, how are you going to calculate? Think about it and give me the answer, right? Since, my dear students, here the coordination number is what? 4. Here the coordination number is 4. So just see that whether it is sp3 or whether it is sp2, and accordingly you will calculate your answer. Okay, yes, I will wait for your answer. I will read your answer in the comment section. Perfect. Let's move forward. You have a few questions, my dear students. These questions actually are very lengthy. So I think I'll do 1 or 2 questions. Rest you can try at your home because we have to discuss many more topics as well. So now let's start the question. The pair in which both species have same magnetic moment spin only value. You have to calculate the same magnetic moment. For same magnetic moment, actually need to calculate the number of unpaired electrons in each and every complex. So this is going to be such a lengthy question. But let's see how are we going to do. Okay, first part, my dear students, A part. I have chromium, I have H2O 6 2 plus. Okay, scandium, titanium, vanadium, chromium 24. So ma'am, chromium atomic number is 24. This is argon 4s2 3d4. Okay, but you will actually write its electronic configuration as 4s1 5. This is how you actually write the electronic configuration of chromium 5. I'm not going to tell you, my dear students. I think you've studied this in your periodic table. Now, what is the oxidation state of chromium here? Ma'am, H2O is a neutral ligand, so its oxidation state is, charge is 0. So the oxidation state of chromium is +2. So it will lose 2 electrons. When it will lose 2 electrons, you will get 4s0, 3d4. So this would be 3d4 and 4s0. Clear? Yes. So now what are you going to do? You just draw these 5 and this is 1. You have 4 electrons and this is 0. If you see, you have H2O. H2O is a weak field ligand, so it will not initiate the pairing. If it is not pairing, ma'am, this means that I need at least 2 vacant d orbitals for the inner orbital complex, but I don't have 2 vacant d orbitals, so the pairing would be what? It would be sp3d2. So the complex would be sp3d2 octahedral, right? Yes, outer orbital complex, and the number of unpaired electrons are 4. So I'll write here the number of unpaired electrons here are 4. Now let's calculate for the second part. Second is cobalt Cl4 2 minus. So if I talk about cobalt's charge, this would be cobalt, my dear students, it is 27 and its charge would be chlorine is -1. So -4, this would go there, then its oxidation state would be +2. So this means that argon 3d7 4s0. I hope you understand this particular part. Now, my dear students, you can very well understand this, that if d orbital has 7 electrons, this means that, ma'am, you will fill the electrons something like 1, 2, 3, 4, 5, 6 and 7. Right, you have 4s here, and since it has Cl, which is a weak field ligand, so no pairing will take place. Again, the complex would be d2sp3, and the number of unpaired electrons here are 3, not 4, 3. So ma'am, here the magnetic moment can never be equal. Perfect? Yes. So this is not the correct answer. This is how you have to do these questions. These are lengthy, but you have to do them fast. Similarly, now let's calculate for the B part. Now let's calculate for the B part. Okay. Chromium, can I do this here only? Let's do it here only. I'll try to do this here only. Chromium, my dear students, H2O is a neutral ligand. So, ma'am, chromium would be +2. Right? Again, my dear students, its atomic number is 24. And if you see 2 electrons are gone, so you will have, I guess, 4 electrons in the d orbital. And since water is a weak field ligand, so here I can say that in chromium part, I'll have number of unpaired electrons as 4, and it would be a outer orbital complex again. If I talk about Fe, my dear students, Fe's atomic number is 26. So Fe is 26, and what would be the oxidation state again? +2, right? +2. And if I write its electronic configuration, then this would be argon 4s0 and 3d 6, 3d6. And if I write the d orbital electronic configuration, 1 2 3 4 5, 1 2 3 4 5 and 6. So I see that unpaired electrons here are also 4. Since both the complexes have, again, my dear students, it would be a outer orbital complex because it has a weak field ligand. But if I see, it has total number of unpaired electrons as 4 in both the cases, and if the number of unpaired electrons are equal, then their magnetic moment will also be equal, right? Yes. So option B will be your correct answer. A pair in which both the species have same magnetic moment, they both will have same magnetic moment because they have the same number of unpaired electrons. Try to calculate in C and D yourself, my dear students. I have given you the idea how you are going to do this, right? If you want to do them fast and fast, you need more and more practice. Perfect. I hope you understand this. Now let's move forward to the next question. The next question is the diamagnetic species. Again, you have to calculate the diamagnetic species. This means that you have to again write all the electronic configuration and see where all the electrons are paired. So now let's see, my dear students, if I talk about this nickel, cadmium, titanium, vanadium, chromium, manganese, iron, cobalt, and nickel. This means that 28 is its atomic number. And if I calculate its oxidation state, it will come out to be +2. If it is +2, then argon, I'll get 4s0 and 3d8. Right? So d orbital, I have how many? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, and 8. I have 8 electrons. Now if I see, then I have 4s0. Right? Yes. Since Cn is a strong ligand, so it will initiate pairing, and pairing will happen, and you will get what? 1, 2, 3, 4, 5, 6, and 7, 8. Right? And you will have S, right? And then you will have 4p as well. So since coordination number is 4, my dear students, so you only need one vacant d orbital. You have one vacant d orbital, you have S, and you have 3 p orbitals. So you will only take 2, that is dsp2. One d orbital, one s orbital, and you will take 2 p vacant orbitals, and you will get hybrid orbital as this dsp2. Now, my dear students, it will be a inner orbital complex because you are using a inner d orbital. Yes, ma'am. And you see that you don't have unpaired electrons. So this means that, ma'am, this is the case where I have diamagnetic complex. So we were very lucky that the first part only came out to be diamagnetic. So option A is your correct answer. In the other parts, you can yourself see that Cl will have is the weak field ligand, so it will not initiate pairing. Cl, weak field ligand, not initiate pairing. Fluorine, weak field ligand, not initiate the pairing. Only and only the strong field ligand would initiate the pairing. Right? Yes. So I hope it's clear. Very good, my dear students. Let's move forward to the next question. Amongst the following, the most stable complex is. Now, my dear students, you are supposed to tell the most stable complex. Try the question yourself. We've studied everything. So I think you can do this question, my dear students. Ma'am will get aside. Try to do this question yourself. So now let's see, amongst the following, the most stable complex is. How are we going to find out the stability? Whenever we talk about the stability, I can only remember, my dear students, the chelation effect. Wherever there would be more chelation, that would be the more stable complex, right? Yes. So if I see here, monodentate ligand, neutral. Ma'am, it is a monodentate ligand, again neutral. Ma'am, it is a didentate ligand, right? Yes, ma'am. So here denticity is present. Here, my dear students, denticity is 2, and if you see where there is denticity 2, one chelate ring will be formed, whereas again Cl is a monodentate ligand. So where is the chelation present? Option C. Who is the most stable complex? Option C. So option C will be your correct answer. This is how you are going to answer these questions. So easy, right? Perfect. Now, my dear students, let's move forward to the next question. Next question is, which of the following is diamagnetic complex? Haven't we done such type of a question? Yes, ma'am, we have done. So, can my students do this question on their own? Yes, ma'am, they can do. So, my dear students, this is going to be your homework again, right? Diamagnetic means you have to see all the complexes. Just look out for the complex where all the electrons are paired, right? Yes, that will be your correct answer. Let's move forward to the next question. Now, next part, I guess. Limitations of valence bond theory. Obviously, every theory has its limitations. So now we are going to talk about the limitations. What are the limitations? It involves a number of assumptions. You have assumed a lot that hybridization takes place, and this is how the ligands overlap on each other. All these were assumptions from the for the theory. It does not give qualitative interpretation of any magnetic data. This is just theoretical limitations, my dear students. So you can just go through them. Okay. It does not explain the color, how the color is exhibited. Various complexes show different types of colors. It never gives any information that how do they give colors, right? Yes, it does not give a quantitative interpretation of the thermodynamics or the kinetic stabilities of the coordination compounds. It just says that chelation gives you stability, but it does not explain how, right? Next, my dear students, it does not explain exact predictions regarding the tetrahedral and the square planar. It does not give any distinction between square planar and tetrahedral complex. Okay. Next, it does not distinguish between the weak field and the strong field ligand. How are you saying that the nitrogen containing compounds would be strong field ligand? How are you saying that the carbon containing compounds would be strong field ligands? Why? What is the reason? It hasn't given you any information regarding this. So these were the limitations, and these limitations will be covered by the crystal field theory, right? Yes. So now we are going to study about the CFT, crystal field theory. According to this, my dear students, the first concept which you talked about in the valence bond theory, that all the ligand and metal do overlap, that is absolutely wrong according to CFT. CFT says that the bonding is actually interactions. It is not overlapping. It is only mere interaction between the metal and the ligand, right? So according to this, attraction between central metal and the ligand in the complex is purely electrostatic. It is nothing related to overlapping of the orbitals. It is merely electrostatic interaction. Okay. According to this, central metal atom or ion is considered as positive charge. It says that the central metal will always have a positive charge, and that is absolutely correct, right? It will accept electrons, oxidation number, and the ligands as the negative charge. Clear? No issues. Ligands are treated as point charges. They have point charges or dipole moments. Ion would be a point charge, and the neutral and the ion would be a point charge, and if it is neutral, then it will have a dipole moment. Clear? Yes. There is no interaction between metal orbital and ligand orbital. No overlapping. There is no overlapping. It is mere electrostatic interaction. Okay. Next is energy of orbital having same energy increases because of the repulsion. This is the most important assumption which we are going to discuss completely. Okay. So now let's start and discuss this particular part. See, you all know that we talked about d orbital, and since in a central metal most of the metals are your d block elements, so their valence shell is their valence orbital is actually d orbital. So we know d orbital or shapes. What are the d orbitals shapes? Let's talk about them. D orbitals, my dear students. See, ma'am, we have different types of orbitals. We have d xy, d yz, and ma'am d x z, right? Yes, you have d x square y square, and you have d z square, right? I think all of you have learned or studied their shapes as well in the atomic structure chapter. If you talk about this, then x-axis, y-axis, and the orbitals are in between the axis, right? Again, if you talk about yz, then ma'am y and z and the orbitals are in between the axis. If you talk about xz, then x and z and the orbitals are ma'am the axis, right? Yes. If you talk about dx square y square, what will happen? X-axis, y-axis, and the orbitals are along the axis. If you talk about dz square, you have z-axis and orbitals are along the axis and a circle like of kind of a thing, right, around the axis. Perfect, my dear. This is the shape. I hope you understand. And we always think about the d orbitals as degenerate. Whenever you are writing d orbitals, how do you write them? You write them like this, right? dxy, yz, zx, x square, y square, z square. It doesn't matter because those are degenerate. They have equal energy. But what does CFT says? CFT says that when ligands come and approach to the metal ion, then the metal ions, these d orbitals, do not remain degenerate. What do? They split out. Their energies changes, and how their energy changes, that is the most important part of C. Imagine, my dear students, you have these d orbitals. You have these 5 degenerate orbitals. Okay. Now, what will happen? What will happen? Imagine if the electrons, if the ligands are approaching along the axis. If the electrons are approaching along the axis, right? Yes. Ma'am, I know that these two orbitals have their electron density along the axis, right? They have the density along the axis, right? If they have the or electron density along the axis, and the electrons, actually the ligands are approaching along the axis only, then ma'am, there will be electron-electron repulsion. I hope you understand this, that if the ligand is approaching from here, then there would be some electron-electron repulsion. And when there is repulsion, there is, what will happen? And when repulsion will take place, instability will take place and the energy will increase, right? So, dx square y square and dz square's energy would increase, right? So, what happens is that this is known as the barycenter. This is known as the barycenter, the center where the energy was degenerate for the orbitals. Now, the ligands started approaching along the axis. If they started approaching along the axis, the energy of dx square, y square and dz square would increase. So, their energy would increase. So, here you will get dx square, y square and dz square, because these were along the axis. And since the electrons are approaching along the axis, then the orbitals which are in between the axis, which means that these three orbitals where electrons are in between the axis, they will have lesser amount of energy now, right? Yes, they would be more stable. So you get 3 orbitals, dxy, dyz and dz. This is how there will be change in energy depending on the ligands. Where are they approaching from? If they are approaching along the axis, or are they approaching away from in between the axis? So now let's discuss if you have understood this concept. So now I think you can understand this part as well. If field produced by the ligands is spherical, if the electronic field is spherical, that is, I told you that about the d orbital, but if it was that axis is common, the electron density is present in all the axes, then ligands might appear from any direction. It will not matter, the energy will definitely increase because repulsion will be present from everywhere, right? Yes. So, it is telling you that if the field produced by the ligand is spherical, symmetrical, just the example of s orbital, then d orbitals remain degenerate, because everyone's energy would increase according same amount, and they will still remain degenerate. Yes, their energy will increase, but that would be same, having higher energy than before. When the field produced by the ligands is not spherical, for example, the d orbital, or symmetric is not spherical or symmetrical, for example, the octahedral, tetrahedral, square, planar, then the degeneracy of the d orbital will definitely change. Now, d orbitals are not affected equally by the ligand field, obviously, if they are approaching along the axis or not, and they split having different energies, and this is known as crystal field splitting. This splitting is known as crystal field splitting. Okay, perfect. Let's move forward. Here is the thing which I told you. Okay, average increase in energy of d orbital in octahedral crystal field. This is the common energy, and this is your zero energy part. This is your barycenter. Or even increases in energy of d orbitals in spherical crystal field. Degenerate orbitals. Now, my dear students, crystal field splitting energy of octahedral complex. In octahedral complexes, my dear students, ligands approach along the axis. So, you can say that in octahedral complex, ligands approach along the axis. Okay. If they approach along the axis, then there would be an increase of 0.6 delta O plus, and here it would be decrease of 0.4 delta O. What is delta O? It is your crystal field stabilization energy of octahedral complex, delta O. right? Yes. So I hope you understand this concept. Perfect. Now let's move forward. There will be repulsion between the electrons. Now it is telling you the same story which I told you, that they will approach along the axis. There will be repulsion and the orbitals would increase. So you just have to revise this concept. See, there will be repulsion between the electrons in the d orbital and the electrons or negative charges of the ligands. Such a repulsion is more than metal d orbital is directed towards the ligand than when it is away from the ligand. Thus, the dz square and the dx square y square orbitals which point towards the axis will along the direction of the ligand will experience more repulsion. Obviously they'll experience more repulsion and will be raised in energy, and the dxy, these orbitals which are directed between the axis, will be lowered in energy related to the average energy in the spherical crystal system, right? Yes, crystal field. This is not spherical, this should just make it right. Perfect. So I hope you got the story. Perfect. Very good, my dear students. Now let's move forward. Now, if you talk about the concept which is your electron filling in d orbitals. Now, my dear students, if we talk about, okay, I think you should take these screenshots. I'll get aside. Let's start now. If we talk about the electron filling in d orbitals, now I have talked about the complexes here. See, this is what it is. If we name these orbitals, what will we name? This would be T2G, T2G orbitals, T2G, and this would be EG orbitals. Why do we use G part here, my dear students? Because G stands for Gerard. Gerard, and Gerard means actually Gerard or Gerard, I don't know how to pronounce it, but that is because it stands for something which is symmetrical. Okay, so something which is symmetrical, you use Gerard or Gerard, and this is how you calculate. If you are supposed to calculate the CFSE value, then that would be equal to number of electrons in the EG orbital. What is n of EG? It is the number of electrons in the EG orbital into, I think, 0.6 into 0.6 minus number of electrons in T2G orbital into 0.4. This will give you the CFSE value and crystal field stabilization energy. This is how you calculate the crystal field stabilization energy. Right? Perfect. Now let's move forward. Now if you talk about the electron filling in d orbitals, my dear students, if you have strong field ligands, again those nitrogen and carbon containing compounds, pairing takes place. Okay, so pairing takes place if you have strong field ligands. If you have weak field ligands, then no pairing takes. So here are the electronic configurations which you have to go through, right? See, if the pairing takes place or not, what will happen? You have the orbitals here, T2G orbitals, and you have two orbitals which are your EG orbitals. If you have a strong field ligand, then my dear students, first, second and third electron, this would be exactly same for your strong field ligand or weak field ligand, it will be same. But the fourth electron, if you have a strong field ligand, then first, fourth electron will be here, then this, and then this, and then this will be filled. Okay, that is in case of strong field ligand, pairing will take place. And if you have a weak field ligand, what will happen? If you have a weak field ligand, my dear students, then the fourth electron will actually go here, then fifth here, and then sixth onwards pairing will take place. So this is something very important which you need to understand, and all the electronic configurations are given here. All the electronic configurations are given here. You can just go through them. Right? Perfect. I hope you got this point. Very good. And G is used for, I think you understand that, Gerard. Now, the configuration is not changing due to the type of ligand. Yes. Why? Because till 3 electrons, it would be same for strong or weak. Nothing matters. Similarly, for when all the electrons are filled, then last 2 electronic configurations would also be same. Perfect. I hope you understand this. Let's move forward. Calculation of CFSE, ma'am just told you that whenever you calculate CFSE, what you have to do, you have to calculate plus 0.6 into number of electrons in EG minus 0.4 into number of electrons in T2G. Clear? Yes. Perfect. Now let's move forward. Next is factors affecting the CFSE. Nature of the ligand. Obviously, if it is a strong field ligand, weak field ligand, pairing will occur or not. That determines that how many electrons will be present in T2 and EG, and similarly, CFSE value will be affected. Other factors are number of ligands, right? Then the type of metal cation, then change on the metal, charge on the metal, ion, and then chelation effect. Okay, all these affects the stability or the CFSE value. Perfect. Now let's move forward, my dear students. If you talk about the tetrahedral complex, my dear students, that was your octahedral complex. In case of tetrahedral complex, what happens is the ligands approach from in between the axis. They do not approach from the axis. Now, if they are approaching from in between the axis, then the orbitals which are in between the axis will experience more repulsion and they'll have higher energy. So since T2 orbitals are those three orbitals dxy, yz and zx are actually along the axis, in between the axis, so their energy would increase. So in case of tetrahedral complexes, what happens? The energy increases upward, and here too, right? Since, my dear students, tetrahedral is not a tetrahedral structure is not symmetrical, so you don't use a G relation for that. Okay, perfect. And it is exactly the same. I think you can understand this. Here delta T would be your tetrahedral CFSE value for your tetrahedral, right? You can calculate similarly how you calculate it for octahedral, and the filling of electrons would always take place. And the most important thing, my dear students, here is that always and always pairing will occur. Always and always pairing will take place. It doesn't matter you have a strong field ligand or a weak field ligand, pairing will always take place in case of tetrahedral or when the coordination number is 4. Whenever the coordination number is 4, pairing will definitely take place. Always remember that. This is most important. In octahedral, you have to see strong field ligand and weak field ligand, but in case of tetrahedral, you don't have to see whether it is a strong field ligand or weak field ligand, right? Perfect. I hope you understand this. Perfect. It is exactly the same. Just understand this concept and you can fill the electrons. Here is the filling of the electrons. You can go through that. Perfect. In tetrahedral coordination entity, the d orbital splitting is inverted and is smaller as compared to the octahedral complex, right? Octahedral field splitting. Consequently, the orbital splitting energies are not sufficiently large, forcing pairing, and therefore low spin configurations are rarely observed. Perfect. Now let's move forward. Now here is a question which you have to do. Which of the following statements is not correct? You have to tell which of the following statements is not correct. Just read the question and we'll move forward. Nickel H2O whole 6 2 plus and nickel NH3 whole 6 2 plus have same value of CFSE. Will they have same value of CFSE, my dear students? Just understand this. If you talk about nickel, nickel's coordination number, oxidation number is manganese, iron, cobalt and nickel, right? It is, ma'am, 28. Now if you see, the oxidation state in both the cases is +2. In both the cases, nickel oxidation state is +2, right? So if I write its electronic configuration, then I will have argon 4s0 3d8. So I have to fill 8 electrons and it is a octahedral complex, so I will have something like this, right? Yes. Now, if I fill 8 electrons for a strong field ligand, let's fill for a strong field ligand 1, 2, 3, 4, 5, 6, 7 and 8. 8 electrons are filled. This is for a strong field ligand. I have written this is for a strong field ligand, that is for NH3 part. Now I will write for H2O part. Okay. Now for H2O part, I will have something like this, 3 orbitals and 2 orbitals, right? Again, 8 electrons. Yes, ma'am. But this time pairing will not take place. So 1, 2, 3, 4, 5. 5. Then 6 and then 7 and then 8. What I see that this is again your weak field ligand. But what happened? Coincidentally, both electronic configurations are exactly same. So I can say that which of the following have same value of CFSE? Yes, they will have same value of CFSE. Though there is pairing in one case and not in the other, but still their value would be same, right? Yes, so this statement is true. Second statement is this and this have the same value for magnetic moment. Do they have same value for magnetic moment? When you calculate the magnetic moment, what do, my dear students? You actually for magnetic moment, you see the valence bond theory. You don't see the CFSE, crystal field theory, you see the valence bond theory. And for valence bond theory, I know that nickel 2 plus will have an electronic configuration of 4s0 argon, and I will have 3d8. 1, 2, 3, 4, 5. Right? Now, if I have a strong field ligand, then pairing will take place. I have 8 electrons. So, ma'am, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. This will be for a strong field ligand. But for a weak field ligand, my dear students, which is your H2O, pairing will not take place. So 1, 2, 3, 4, 5, 6, 7 and 8. Here 2 unpaired electrons are present, but in the case of strong field ligand, no unpaired electrons are present. So their magnetic moments will be different. So this statement is actually false, right? So we see that for CFSE, you have to go through the crystal field theory and you have to calculate accordingly, and for the magnetic moment you have to calculate it like this, and we see that only statement A is correct, so option A will be your correct answer. So this is how you are supposed to solve the questions. Perfect, my dear students. Let's move forward. Next is the color of the complex. The color of the complex is a very small part in your NCRT also, and majorly the questions are asked, very easy questions are asked. So if we talk about the color, what happens actually is that if you have, let's say you have octahedral complex and you have 3 orbitals, here you have only 2 orbitals. So what happens, my dear students? What happens here is that you have 3 orbitals, you have 2 orbitals here, and let us say that you have an electron present here. What will happen, that this electron will accept some energy and it will move upward. Okay, now once this electron has accepted some energy and moved forward, what will happen? It will go there. Now when you have high energy, you move here and there to your friends, to your relatives, but at the end when you are stable, you come back to your home, right? So this electron will definitely come back to its home. Now when this electron comes back to its home, it emits out some energy. It emits out some energy of a particular wavelength, and that energy will give you the color, and that energy would actually give you the color. So how the complexes are colored? When they are only and only colored when DD transition is. If you have vacant, if you have an unpaired electron, if you have an unpaired electron and that unpaired electron has a vacant orbital to go up and come back down, that is the reason you can observe color. If you don't have any vacant orbital, then there would be no transition taking place, right? Yes. So the color of the complex is complementary to that which is absorbed, and the color in the coordination compounds can be readily explained in terms of the crystal field theory. Okay. See, if configuration of central metal is from D1 to D9, if they have D1 to D9 electronic configuration, they have an electron, they have a vacant orbital, you will definitely see DD transitions and the complexes will be colored. But if you have D0 or D10 electronic configuration, if you don't have any electron, how can DD transition take place? If you have all the orbitals completely filled, how the transition will take place, right? Yes. So these two are the configurations where no transition takes place, and so you cannot observe color. But D1 to D9 electronic configurations will definitely show you electronic configuration. Okay, DD transition is D1 and this N, right? Yes. So I hope you got this point. Very good, my dear students. Perfect. Let's move forward. Now, sometimes a question is asked that CuSO4 is colorless, but CuSO4.5H2O is colored blue. Why, my dear students? So here, what are you going to say? That CuSO4 is not a complex. Not a complex. It is not a coordination compound. Okay. So if it is not a coordination compound, no DD transition will take place. But if you talk about CuSO4 5H2O, it is a complex. It is a coordination compound. And if it is a coordination compound, then ma'am, it definitely has DD transition possibility and the complex is colored, right? Perfect. Very good. Let's move forward. What are the limitations of crystal field theory? Bonding between metal and ligand, right? Strength of ligand is not explained. So these are a few limitations of crystal field theory. You can just go through them. Perfect. Now, my dear students, we are going to discuss about a very, very important part, which is your isomerism. Now we are going to discuss about the isomerism. What is isomerism? You have studied about isomerism in organic, right? So it is exactly the same. When you have the same molecular formula, but the arrangements are different, you call them as isomers, right? Yes. Now there are two different types of isomerism. Maybe the linkages are different. Maybe the linkages are different, right? Then they are known as your geometrical isomerism, right? Those are known as your structural isomerisms. And when the uh, 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 molecular formula is same and the linkages is also same, but only the orientation is changing, then that calls for your stereoisomerism. Okay, so basically there are two types of isomerism. We'll be discussing all of them. Isomerism are two or more compounds that have the same chemical formula but a different arrangement of atoms. Because of the different arrangement of atoms, they differ in one or more physical, chemical, or chemical properties. Okay, yes, we'll talk about them slowly and slowly. Okay, now I told you there are two types of isomerisms. One is your stereoisomerism, one is your structural isomerism. In stereoisomerism, you get geometrical isomerism and you get optical isomerism. Okay, so we're going to discuss all together. Structural isomerism. Now, the major difference between stereoisomerism and structural isomerism is, here, my dear students, linkages are different. Here, linkages are different. But if you talk about the stereoisomerism, the linkages, the bonds, everything is same. Only and only what changes is the orientation. The orientation, that is the direction of the bonds, changes. The linkages never change, only the direction changes, only the orientation changes. Okay, yes, I think you can understand this part from your organic chemistry as well. So I'll not go into deep a lot because we have to cover the complete chapter today. Okay, now let's move forward. One by one, we'll talk about the structural isomerism. Structural isomerism is the isomerism where the linkages are different. Okay, what are the different types of structural isomerisms? Ma'am is going to you. The first type is your linkage isomerism. What is linkage isomerism, my dear students? When the linkage changes. When the linkage changes. Linkage isomerism arises by the ambidentate ligands. Obviously, let us say you have SC. Let's talk about NO2. Okay. In NO2, you have nitrogen as the linkage, or it could be ONO linkage, right? Yes. So, my dear student, maybe in one particular complex, let's say you have something cobalt, NO2, and Cl5. Okay, let's say one complex is this and the other complex is cobalt, ONO, and let's say Cl5. Okay, these are the two complexes. My dear students. If you see, everything is same. Molecular formula is also same. Here the linkage is nitrogen and here the linkage is through oxygen. So it is a linkage isomerism, and linkage isomerism only and only arises by the ambidentate ligands. If ambidentate ligands are not present, then everything is same, right? Yes. So ambidentate ligands gives rise to the linkage isomerism. Next is your coordination isomerism. What does coordination isomerism stands for? This type of isomerism arises from the interchange of ligands between the cationic and the anionic entities of different metal ions present in a complex. Let us say you have a complex where you have both cation and anion as coordination pairs. Let us say here you have CO, NH3, whole 6, and here you have CO, not CO, let's say chromium. Here you have chromium and H2O, whole 6. This is your one compound, and if the other compound is CO, H2O, whole 6, and here you have chromium, NH3, whole 6. So what is happening? Only the ligands have changed. Right? In the coordination spheres. So the molecular formula for both the complexes will still be same, but the linkages again are different because of the coordination spheres, and that is what is known as your coordination isomerism. Okay, so this type of isomerism arises from the interchange of ligands between the cationic and anionic entities of different metal ions present in a complex. Perfect. Let's move forward. Next question. Next isomerism. Okay, coordination again. Let's move forward. Ionization isomerism. Now, when you talk about ionization isomerism, my dear students, sometimes what happens is, let us say you have a complex CO, NH3CO, NH, you have Cl, and this is 5, and you have bromine outside, and you have a complex where you have CO, NH3, bromine, and here you have chlorine. Now, if you will ionize them, if you will put them into aqueous solution, what will you get? You will get CO, NH3, and you will get bromine ion. Here, what will you get? You get CO, NH3, bromine, and here you will get Cl minus as your ion. So molecular formula is still the same, but what is the changing is the outside anion, outside anion. Such such compounds are actually as your ionization isomers. Okay, so let's see. This form of isomerism arises when the counter ion in a complex salt is itself a potential ligand and can displace a ligand which can then become the counter. Right? Yes. So I hope you get this. Perfect. Very good, my dear students. Let's move forward. Next is your solvate isomerism. In this case, my dear students, only and only what happens is that the ion which is getting exchanged is water. When you have water as your changing ion, you call it as solvate isomerism. It is exactly the same as your ionization isomerism, but only when water is involved, you call it solvate isomerism. This form of isomerism is known as hydrate isomerism or solvate isomerism. In case where water is involved as a solvent, this is similar to the ionization isomerism. As ma'am told you, this is similar to the ionization isomerism. Solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal ion, rarely present in free solvent molecule, the crystal lattice. So it is exactly the same as your ionization isomerism, only when you use water as the ligand or as the ionization part, anion part, you call it as hydrate isomer or solvate isomer. Right? Perfect. Very good. Let's move forward. Now we are going to talk about the stereoisomerism. In stereoisomerism, the most important part, my dear, from where most are asked, you have geometrical isomerism. What is geometrical isomerism? When the bonds are exactly the same, the orientation changes, only the orientation changes, only the direction changes. And in this case, you actually find out cis and trans forms. What is a cis form? When two ligands are at a 90-degree angle. And what is trans form? When the two ligands are at the 180-degree angle. Okay, so now let's talk about this. This type of isomerism arises in the heteroleptic complexes. Obviously, it will always exist in heteroleptic complexes. Okay, perfect. Due to different possible geometric arrangements of the ligands. Tetrahedral complexes do not show geometrical isomerism. Why do tetrahedral complexes do not show geometrical isomerism? Because the tetrahedral geometry, I think you have studied in your chemical bonding chapter. The tetrahedral geometry is something like this, where all the angles are at 109 degree 28 minutes, right? Yes. So if all the ligands are at 109 degree 28 minutes, you cannot find which is at 90 degree, which is at 180 degree. Cis and trans are not possible here. That is the reason it does not show structural isomerism. Whereas if you talk about square planar geometry, the square planar geometry is something like this. Right? So here, if I talk, I can say that this angle is 90 degrees, so it can form cis form, and this whole angle is 180 degrees, so I can see that trans and cis form exists. So yes, this can show geometrical isomerism. If we talk about octahedral geometry, M, you have x here, 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 and here as well. So this is your octahedral geometry. This is up and this is down. If you see, you can find out that, and this is 90 degrees. So we can see that yes, here also cis form can exist. Also transform can exist 180 degrees. Yes. So octahedral and square planar. I'll write this. So geometrical isomerism. But tetrahedral does not have the angles. So this does not show iso. Okay. Tetrahedral complexes do not show geometrical isomerism because the positions of the unidentate ligands attached in the central metal atom are the same with respect to each other. Okay, perfect. Let's move forward. Stereoisomerism. Stereoisomerisms is, you have studied about this in organic part, my dear students. So you have to study there as well. So I'll not discuss it in very detail. So just study this. Stereoisomers have the same chemical formula, obviously, and they have the same chemical bonds as well. But they have different spatial arrangements. They have its different spatial arrangements. Okay. Now, optical isomerism. Optical isomerism, my dear students, what does it say? Optical isomers are, what are optical isomers? Those are the mirror images of each other, and that too non-superimposable. They are not superimposable to each other, right? Yes. So, optical isomers are mirror images. I hope you understand this. If I am talking about this hand, the mirror image of this hand is, just a second. The mirror image of this hand is this. And if I talk about their superimposable part, then it is not superimposable. So they are optical isomers. So what are optical isomers? Which are mirror images of each other, but they are non-superimposable. So the optical isomers are mirror images that cannot be superimposed on one another. These are called enantiomers as well. The molecules or the ions that cannot be superimposed are called chiral. I hope you understand this. The two forms are called dextrorotatory or levorotatory, which is experimental. You cannot give which is dextro or which is levo, and nobody is going to ask you, at least in coordination. Okay. Depending upon the direction, they rotate the plane polarized light. Generally, it is said that which rotates the plane polarized light to the left side, it is levorotatory. To the right side, that is your dextrorotatory, right? Yes, this is more of organic part. No one is going to ask you in coordination chemistry. Perfect. Let's move forward. At optical isomers, if the compound is asymmetric, if the compound is asymmetric, my dear students, if the compound is symmetric, okay, if the compound is symmetric, plane of symmetry or center of symmetry or both are present, then they are optically inactive. If the compound is asymmetric, plane of symmetry or center of symmetry both are absent, that is, they are chiral, then they are optically active, right? Yes, so this is what you are actually revising your organic. Okay, yes, perfect, my dear students. You can note this down and then we'll move forward. So now we are going to talk about, first we are going to find out that how cis and trans works, and I think optical isomerism is understood. The optical isomerism would be shown only and only if they are mirror images to each other, and also if they are non-superimposable, right? Yes, only then optical isomerism is possible. We'll do some examples, don't worry. Now students, let's move forward again and let's come to the cis and trans form. Okay, so I know that in tetrahedral, no cis transformations are possible, right? Yes, so we will talk about square, planar and octahedral geometry. So now, if we talk about the square planar geometry, square planar, what will be square planar geometry? Ma'am, it would be M. Here you will have a complex A, then here A ligand, then here A ligand, and here A ligand. Okay, yes ma'am. Or I could say, let's say it is 1, 2, 3 and 4. Okay. Now my dear students, let's discuss about this. If you have a complex of the form MA4, where you have all the ligands symmetrical, then if you write the ligands anyhow, be it A here, A here, A here, since the ligands are same, there would be nothing called as cis or trans, right? All the ligands are same, you cannot differentiate, so no geometrical isomerism is shown here. So no geometrical isomerism is possible here. If we talk about the second part, which is, let us change one ligand. Let's say it is 1Ma3B. What will happen here, my dear students? What can you do? Ma'am, we will have a metal. We will have a metal, and then we will have 3 ligands, A, and then we'll have 1 B ligand. Now, if I write B here or here or here, B with respect to all the A's, there will be no change, right? Yes, because only one ligand is different. So, ma'am, here also no cis trans possible, so no geometrical isomerism is possible here. Now, if I talk about the third part, which is Ma2B2 form. So, now what will be the possibility? If you talk about this, you will have metal here, right? You will have A here, you will have A here, you can have B here, and you can have B here. One is this possibility. What is the other possibility, my dear students? Ma'am, M here, A here, B here, A here, or B here. Okay. So if you see here, A and A are at 90-degree angles. Here B and B are at 90-degree angles. And here A and A is at 180-degree angle. So my dear students, this is cis and this is trans. And this is your geometrical isomerism possible. This is how you are going to calculate this. Now let's move forward. What happens if you have something like M, A, B, C? All the 4 ligands are different. Then what will happen? Then, my dear students, you can say that, ma'am, we can write metal here. You just write A here. Always write A here. You can have B, C and D. What would be the other possibility? You can write metal here. You just fix the position of A again. Now you can say that this would be B. Ma'am, here it would be. So B is here, C, and here D. What is the other possibility, my dear students? Again, ma'am, M, fix A. This time, my dear students, D would be at transposition. So you can say, ma'am, D would be at transposition. B would come here and C would come here. So yes, this will also show me geometrical isomerism. You fix one position, you have fixed A position, my dear students. And with respect to A, all the other ligands are changed. And you can see that, yes, geometrical isomerism can be shown here as well. So yes, ma'am, geometrical isomerism is possible here as well, right? Yes, very good, my dear students. So these are the types of isomerisms that can be seen in square planar complex. Now let's talk about the octahedral complex. Octahedral complex. When is octahedral complex shown? When coordination number is 6. And when is square planar shown? When the coordination number is 4, right? Yes. Now, if we talk about octahedral, first possibility would be Ma6. Can we see any type of geometrical isomerism? No, ma'am. So, no geometrical isomerism can be seen here. If we talk about the other form, Ma5B, will there be any geometrical isomerism? No, ma'am. So, no geometrical isomerism, right? If you write the structure, I have not given you the structure of octahedral complex. You have M here, you have A here, you have A here, A here, A here, A here, and A, right? Yes, perfect. I hope you get this idea. This is what is square planar structure. These are in the same plane, and this A is above the axis and this is below the axis. Perfect. Now, what is the third form? Third could be, ma'am, Ma4B2. What are we going to do here? My dear students, if you write M here and you get A, and here you have B and here you have B. So, what can I say? Ma'am, you can say that here the angle is 180 degree. So, this is trans with respect to B. We can only calculate with respect to B. So, this is trans. Now, let's talk about the other part. You have M here. Let's say B and B are present here. A is present here, A is present here, A is here, as well as A is here. So, if you join all these, what can you say? Ma'am, here the angle between B and B is 90 degree. What is it? It is 90 degrees. So this is cis. So yes, geometrical isomerism is possible here. Perfect. Let's move forward. What would be the other type that is possible? Fifth, my dear students. If you talk about the fifth part, that would be M A3B3. I hope you're understanding here. A and B are monodentate ligands, right? Yes. Now you will have M here. You will have M here. There are two possibilities. If all A's are in the same plane, right? Here is B and here is, my dear students, here is B. Clear? Just a second. If you have M here, have A here, have A here, have B here, here as well. Right? Yes. One possibility is this. What is the other possibility? The other possibility is you have M, A, 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 you have B, and you have. So, my dear students, what do you here? Ma'am, when all the ligands, my dear students, when all the ligands are not in the same plane. If you see this, then these ligands are not in the same plane, right? It is forming a different shape. Here also it is forming a different. Here is a different shape, right? Yes. So, when all the ligands are not in the same plane, you actually call them facial. You actually call it a facial. So, here a different type of isomerism is seen, which is known as facial. So, you write it as FAC, F-A-C. And when one type of ligand, if you see A, and A, it is in the same plane. If one type of ligand is in the same plane, then you call it as meridional. So it is given by MER. This is your meridional configuration. This is your meridional configuration, right? Yes. So when A3B3 kind of complex is given, it shows the geometrical isomerism in a very different way, which is your facial and meridional form. Okay, so facial form is when the ligands, none of the ligands are in the same plane. No two ligands are, no all the three ligands are in the same plane, but here A is in the same plane. That is the reason we call it meridional, and it only exists in this form. It only exists in this form. Okay, perfect. Let's move forward. Next, my dear students, 5 and 6. 6 can be M, En whole twice, B2. Here, my dear students, I'll write it as AA. What will I say? Ma'am, AA is a didentate ligand. So it has a denticity of 2. So it has 2 donation sites. And B is a monodentate. It is a monodentate. So B is your monodentate ligand. So what are the possible geometrical isomerisms here? So if you see, you can have a possibility that A and A, since it is a didentate ligand, it can be like this. A and A will be like this. You will have B here, you will have B here. So ma'am, I can see that B is trans to B and this ligand, didentate ligand, is trans to itself. So ma'am, I can say that this is a trans form. And if I talk about the cis form, what will be the cis form? You can draw it very easy. Now you have M, right? You can say that A form is something like this, and you will have A form like this, right? And then you can have B this side, and you can have B this side, and this. Right? Yes. Is this the possibility? Now they both are cis to each other. They both are cis to each other. So this means that which geometrical isomerism is seen? Cis. So these are the different types of complexes in octahedral and square planar form which can show geometrical isomerism. So you see the complex, which is showing these types of, just arrange them to the general type of the complex we have discussed and see which isomerism is shown by them, right? Yes, so I hope you got this idea. Very good. Let's move forward. Let's move forward and solve some questions. Okay, so the first question is, which of the following isomerism is exhibited by the complex? Now you have to tell me which isomerism is shown by the complex. So I'll move I'll move out of the view and you have to do this. Pause the video, try yourself. If I see, then what can I say? When is ionization isomerism seen? When you have a different ion outside the complex, but I don't have any other ion outside the complex. So ma'am, this cannot show ionization. Okay. Hydrate isomerism is shown when you have water. Is anywhere water as a ligand seen? No ma'am. So hydrate is also not. Linkage isomerism is shown only and only by ambidentate ligand. Does it have ambidentate ligand? Chlorine, OH, NH3? No. No ambidentate ligand is present. So this is also not the possibility. So only possibility is geometrical isomerism. So if I see, it is the octahedral complex because here the coordination number I can see is 6. And if I see, then which geometrical isomerism can be seen? Obviously, cis and transform will be seen, because if you see, you have a metal and you have this, let us say A2 type, B2 type and C2 type. So you can once, what can you do? You can write chromium this side. One time you can write chlorine and chlorine trans to each other. Then you can write OH, OH, and you can write NH3, NH3. So ma'am, this would be a transform. And if you talk about the cis form, then you can write it like this as well. So different forms are possible. But since I am making this to be a trans, so I'll represent all of them trans. You can just draw the geometrical isomers with reference to any two ligands. Okay, they need to be similar, obviously. So this is written here. So if we talk about the cis form, what will be the possibility, ma'am? Chromium, chlorine, chlorine. You can write OH. You can write OH. You can write NH3, and you can write NH3. So this is a cis form. So yes, geometrical isomerism is perfect. Yes, let's move forward. Next question, my dear students. Now, the next question is in front of you. You have to just you have to analyze this question and answer the question. Well, so the question is, the arrangements are shown for the complex this. Which one is the wrong statement? You have to give the wrong statement. Okay, let's see the complexes and right statement. Which is the wrong statement? It says 1 and 2 are geometrical isomers. For geometrical isomers, I want to see cis and transformer. So 1 is this and 2 is this. So if I see here, I can say that here bromine and bromine are cis and here bromine and bromine are trans. So yes ma'am. Yes ma'am, we can say that these do show geometrical isomerism. So this statement is absolutely true. Second, 2 and 3 are optically active isomers. For optically active isomers, I know that they need to be mirror images of each other and non-superimposable. So 2 and 3, in bromine, bromine NH3. Is this a mirror image? No ma'am, they are not the mirror images of each other. So this statement is wrong. 2 and 3 are optically, this statement is wrong. 2 and 3 are optically active isomers. No, they are not mirror images of each other, my dear students. Now, let's move forward. 1 and 3 are optically active isomers. Are they optically active isomers? Let's see. Bromine, 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 NH3, bromine, NH3. I think there is something wrong or what? Yes, my dear students, if you see 1 and 3, they are actually mirror images of each other and they are non-superimposable. If you impose them to that side, they will be non-superimposable. So if they are mirror images and non-superimposable, this means that they are absolutely optically active. So yes, ma'am, this statement is correct. Let's talk about the last statement. 2 and 3 are geometrical isomers. Are 2 and 3 geometrical isomers, my dear students? Let's see. Bromine, bromine trans and bromine, bromine. Yes, ma'am. They are geometrical isomers. So only one statement is wrong and we were supposed to give the wrong statement. Which is the wrong statement, ma'am? Option B. So option B will be your wrong statement. Perfect. Let's move forward to the next question. So now let's move forward to the next question. Next question says that the correct order for the stoichiometries of AgCl formed when AgNO3 in excess is treated with the complexes. Okay, so now let's see the correct order of the stoichiometries of AgCl formed when AgNO3 in excess. Now you have AgNO3 excess in excess. Okay, so if you have COCl3.6NH3, okay, my dear students, and you have AgNO3 in excess, so what will be the result? You have AgNO3 in excess and you have Cl3 present here. So ma'am, CO will have all the 6 NH3s here. And what will you get, my dear students? You will get 3 moles of AgCl, right? No issues, perfect. Let's move forward to the second part, which is COCl3 5NH3. So if I talk about COCl3 5NH3, what will I get? Plus AgNO3. Ma'am, you need to satisfy the coordination number of CO, which is 6. So you have NH3 5. So you need one ligand extra. So you will take Cl from here. So you will get only 2 moles of AgCl here. I hope you understand this. Next, my dear students, third part, you have COCl3 dot how many? 4 NH3s, right? Plus you have AgNO3 in excess. So you need to satisfy this CO, NH3 4. Obviously you will have Cl2, right? So you will be left with 1 mole of AgCl. You will be left with 1 mole of AgCl. So how many moles of AgCl? You will have 3, 2 and 1. So 3, 2 and 1, that is option C will be your correct answer. Okay. Even today we have discussed all the questions which are EYQs. So my dear students, you need to understand how the questions are asked and you have to answer them accordingly. Perfect. Let's move forward. And with this, we came to the end of our session. So I hope you got each and every point of this interesting chapter. It is amazing that if you please let me know in the comment section, first of all, that how many questions you answered correctly. Okay, that would really make me feel happy. And then if any of the concept is not cleared, go through the concept again. It is a very interesting and very scoring chapter. So we'll meet in the next session. Till then, keep studying. All the best. Thank you so much.